Look up at the night sky, and you'll see wandering points of light that have captivated humanity for millennia. We call them planets, from the Greek word planets, meaning wanderers. And for thousands of years, we thought we understood them. But what if everything you learned about planets in school was just the beginning of the story? What if these familiar worlds harbor secrets so extraordinary that they read like science fiction? What if the very definition of what makes a planet is still being rewritten by discoveries that shatter our cosmic assumptions? From ice hiding in the shadow of hell itself, to diamonds raining from alien skies, to worlds that shouldn't exist according to our best theories. The universe of planets is far stranger, more violent, and more wonderful than we ever imagined. Today, we're going on a journey through 31 mind-blowing facts about planets that will completely change how you see these wandering worlds. Some will challenge everything you thought you knew. Others will reveal that truth is indeed stranger than fiction. Join me as we explore the most shocking, beautiful, and impossible realities of planetary science. Before we begin this cosmic adventure, I'd love to know, what corner of our planet are you watching from right now? And what time is it where you are? Drop your location and local time in the comments below. Let's start with a contradiction that seems to defy logic itself. Picture Mercury, the closest planet to our sun, where surface temperatures soar to 800 degrees Fahrenheit, hot enough to melt lead. Now, what's the last thing you'd expect to find there? Ice. Billions of tons of it. This isn't some cosmic joke. Deep within Mercury's polar craters lie deposits of water ice that have survived for millions, possibly billions of years. How is this possible on a world that should, by all rights, be a scorched, airless wasteland? The answer lies in Mercury's unique relationship with shadows and sunlight. Mercury's rotation axis is nearly perpendicular to its orbital plane. It has virtually no axial tilt. This means that, at its poles, crater rims cast permanent shadows into their depths. These shadowed regions never see sunlight, creating what scientists call cold traps. In these perpetually dark crater floors, temperatures plummet to -300 degrees Fahrenheit, colder than Pluto's surface. Water ice delivered by ancient comet impacts has accumulated and remained frozen for eons, protected by the very geography of the planet. But here's where it gets even more fascinating. NASA's Messenger spacecraft didn't just detect ice. It found organic compounds mixed with the frozen water. These carbon-based molecules, the building blocks of life, are preserved in one of the most extreme environments in our solar system. Mercury, the planet we thought was nothing but a dead, baked rock, is actually harboring some of the same materials that made life possible on Earth. The discovery reveals something profound about our solar system. Even in the most seemingly hostile environments, the ingredients for complexity and possibly life can find refuge. Every planet holds surprises that challenge our assumptions about what's possible in the cosmos. This cosmic contradiction on Mercury sets the stage for everything we're about to discover. If ice can survive on the planet closest to the sun, then clearly we need to prepare ourselves for a universe where the impossible becomes routine. From Mercury's hidden ice, we travel to Venus, Earth's twin, that couldn't be more different. Here, we encounter another mind-bending planetary behavior that defies our expectations of how worlds should work. Venus spins backwards, while almost every other planet in our solar system rotates counterclockwise when viewed from above the North Pole. Venus rotates clockwise. Astronomers call this retrograde rotation, and it's like watching a clock run in reverse. But Venus takes this cosmic rebelliousness even further. It rotates so slowly that a Venusian day, one complete spin on its axis, lasts 243 Earth days. Meanwhile, Venus completes one orbit around the Sun in just 225 Earth days. This means that on Venus, a day is actually longer than a year. Imagine living on Venus. You'd experience sunrise in the west and sunset in the east, but you'd have to wait 8 Earth months between them. By the time the sun set, Venus would have completed more than one full orbit around the Sun. What caused this bizarre behavior? Scientists believe Venus suffered a catastrophic collision early in its history. A massive object, perhaps as large as a small planet, struck Venus with such force that it not only reversed its rotation, but also slowed it to a crawl. The impact was so violent, it may have stripped away Venus's original atmosphere and any water it once possessed. The backwards, sluggish rotation also affects Venus's magnetic field, or rather, its lack of one. Unlike Earth, Venus has no significant magnetic field to protect it from solar radiation, partly because its slow rotation fails to generate the dynamo effect that creates planetary magnetism. Venus reminds us that planetary evolution is not always gradual and predictable. Sometimes, cosmic violence reshapes worlds in ways that echo across billions of years. Now, let's turn our attention to something so familiar, we rarely think about its strangeness: our moon. Every night, we see it hanging in our sky, but what we're actually looking at is one of the most unusual planetary partnerships in the solar system. Our moon is massive, not just in absolute terms, but relative to Earth itself. With a diameter about 1/4 that of Earth, our moon is proportionally larger compared to its parent planet than any other moon in the solar system, except for Pluto's moon Charon. Most moons are tiny compared to their planets, like pebbles orbiting boulders. But our moon is so substantial that many astronomers consider Earth-Moon to be a double planet system rather than a planet with a satellite. But the moon's influence goes far deeper than tides. Our planet's 23.5-degree axial tilt, which gives us our seasons, without our massive moon, Earth's tilt would vary chaotically over millions of years, causing dramatic climate swings that would make complex life nearly impossible to sustain. Computer simulations show that without the moon, Earth's axis could tilt anywhere from 0 to 85 degrees over geological time. Imagine Earth tilted like Uranus, with its poles alternately pointing toward and away from the sun. The climate chaos would be unimaginable, boiling summers and frozen winters lasting decades, making our planet inhospitable to the stable conditions life requires. How did we get such an unusually large moon? The leading theory is spectacular. A Mars-sized object called Theia collided with the early Earth about 4.5 billion years ago. This impact was so massive, it vaporized both Theia and a large portion of Earth's crust and mantle. The debris from this collision formed a ring around Earth, which eventually coalesced into our moon. This giant impact theory explains many puzzles about the Earth-Moon system: why the moon has a small iron core relative to its size, why Earth and moon have similar oxygen isotope ratios, and why the moon's orbit is tilted relative to Earth's equator. The collision that created our moon was one of the most important events in Earth's history. Without it, our planet would be a very different world, spinning faster, wobbling chaotically, experiencing extreme tidal changes, and possibly never developing the stable conditions that allowed complex life to flourish. When you look up at the moon tonight, you're seeing the result of cosmic violence that, paradoxically, made our peaceful, life-bearing world possible. We are the children of catastrophe, and our moon is the witness that hangs in our sky every night, reminding us of the extraordinary events that shaped our cosmic home. From Earth's stabilizing moon, we journey to Mars, the red planet that continues to surprise us with its geological extremes. Hidden beneath the rusty dust of this seemingly quiet world lies evidence of volcanic activity so massive it dwarfs anything on Earth. Meet Olympus Mons, a mountain so colossal that it challenges our understanding of what's possible in planetary geology. Rising 13.6 miles above the Martian surface, Olympus Mons towers nearly 3 times higher than Mount Everest, but its height is just the beginning of its mind-boggling statistics. This volcanic giant covers an area roughly the size of Arizona, about 114,000 square miles. To put this in perspective, you could fit the entire state of New York inside its base with room to spare. The volcano's slopes are so gradual that if you were standing on Mars at its base, you wouldn't even realize you were looking at a mountain. The peak would be hidden beyond the horizon, invisible due to the curvature of Mars itself. Olympus Mons is what's called a shield volcano, built up by countless lava flows over millions of years. Its gentle slopes, typically only 2.5 degrees, tell the story of repeated eruptions that sent rivers of molten rock flowing for hundreds of miles across the Martian landscape. But here's what makes Olympus Mons truly extraordinary. It grew to this impossible size because Mars lacks plate tectonics. On Earth, our continents drift over hotspots in the mantle, preventing any single volcano from growing too large. The Hawaiian island chain formed this way as the Pacific plate moved over a hotspot. It created a string of volcanoes rather than one massive mountain. Mars, however, has no moving crustal plates. When volcanic activity began at the location that would become Olympus Mons, the crust stayed put. For potentially hundreds of millions of years, lava erupted from the same spot, building layer upon layer, flow upon flow, until it created this geological monster. The volcano's summit contains a complex of 6 overlapping calderas. Circular depressions formed when magma chambers emptied and collapsed. The largest calderas is 50 miles across and over a mile deep, large enough to swallow entire cities. These calderas formed during different periods of volcanic activity, creating a nested structure that records Mars's geological history. Evidence suggests Olympus Mons may have been active relatively recently in geological terms, perhaps as recently as 25 million years ago. While this might seem ancient, it's practically yesterday in planetary timescales. Some scientists speculate the volcano might even be dormant rather than extinct, waiting for the right conditions to roar back to life. The existence of Olympus Mons reveals something profound about Mars's past. This wasn't always the cold, dry world we see today. Billions of years ago, Mars had a thicker atmosphere, flowing water, and intense geological activity. The massive volcanoes of the Tharsis region, including Olympus Mons, pumped enormous amounts of gas and dust into the Martian atmosphere, temporarily warming the planet and perhaps making it more hospitable to life. Today, Olympus Mons stands as a silent monument to Mars's more dynamic past, a giant that grew in the absence of the geological recycling that limits mountain building on Earth. It's a reminder that different planets can evolve in dramatically different ways, creating wonders that exist nowhere else in our solar system. When future human explorers reach Mars, they'll see Olympus Mons rising from the horizon like a wall reaching towards space. A mountain so large it defines the very geography of an entire planet. Leaving the geological wonders of Mars behind, we venture to the true giant of our solar system, Jupiter. This massive world doesn't just dominate through size alone. It plays a crucial protective role that has shaped the evolution of life on Earth in ways we're only beginning to understand. Jupiter is our solar system's gravitational guardian, acting like a cosmic vacuum cleaner that sweeps up dangerous debris before it can threaten the inner planets. With a mass greater than all other planets combined, Jupiter's immense gravitational field extends its influence across vast regions of space, fundamentally altering the trajectories of comets, asteroids, and other potentially hazardous objects. Consider the raw numbers. Jupiter contains more than twice the mass of all other planets put together. Its gravitational influence reaches far beyond its visible atmosphere, creating what astronomers call its Hill sphere, a region of space where Jupiter's gravity dominates. This sphere extends about 53 million miles from the planet, creating a gravitational net that captures or deflects objects that might otherwise hurtle toward Earth. The most dramatic example of Jupiter's protective power occurred in 1994 when comet Shoemaker-Levy 9 collided with the giant planet. Astronomers worldwide watched in amazement as more than 20 fragments of the comet slammed into Jupiter's atmosphere, creating dark scars larger than Earth that remained visible for months. Each impact released energy equivalent to millions of nuclear bombs, demonstrating the catastrophic damage such an object could inflict on our world. But Jupiter's protective role extends far beyond capturing the occasional comet. Computer simulations show that without Jupiter's gravitational influence, Earth would be bombarded by asteroids and comets at a rate 100 to 1,000 times higher than we currently experience. The late heavy bombardment that scarred the Moon and early Earth about 4 billion years ago would be a constant, ongoing process. rather than a discrete historical period. This protection has been crucial for the development of complex life on Earth. While some asteroid impacts may have delivered water and organic compounds necessary for life, too many impacts would sterilize our planet's surface repeatedly, preventing evolution from progressing beyond simple microorganisms. Jupiter's gravitational shepherding has provided Earth with the Goldilocks level of impacts. Not too many, not too few, but just right for life to flourish. Jupiter's influence on our solar system's architecture goes even deeper. The giant planet helped shape the asteroid belt between Mars and Jupiter, preventing the rocky debris there from coalescing into another planet. Jupiter's gravity stirs this region constantly, keeping asteroids in motion and occasionally flinging them toward the inner solar system or out toward the outer reaches of space. Recent research has revealed that Jupiter's protective influence isn't just about gravity, it's also about timing and location. The giant planet migrated inward toward the Sun during the early solar system's formation, then migrated back outward in what scientists call the Grand Tack model. This migration scattered planetsimals and helped determine which materials ended up where in our solar system, ultimately influencing the composition and habitability of Earth. However, Jupiter's protection isn't perfect or permanent. The planet's gravitational influence can sometimes work against us, nudging objects from the outer solar system into Earth-crossing orbits. Some of the asteroids that pose potential threats to Earth have been gravitationally scattered by Jupiter's influence over millions of years. Moreover, Jupiter's protective role may change over time. As the solar system ages and Jupiter's orbit slowly evolves due to gravitational interactions with other planets, its ability to shield Earth may increase or decrease. Understanding these long-term dynamics is crucial for assessing Earth's future safety from cosmic impacts. The story of Jupiter as our protector reveals something profound about planetary systems and the development of life. The presence of giant planets in the outer regions of a star system may be essential for creating stable, habitable conditions on inner, rocky planets. As we discover more exoplanetary systems, we're finding that Jupiter-like giants are common, suggesting that gravitational protection might be a widespread feature of planetary systems throughout the galaxy. When you look at Jupiter through a telescope or see it as a bright star in the night sky, you're seeing more than just another planet. You're looking at our cosmic bodyguard, a massive world whose gravitational embrace has shaped the conditions that allowed life on Earth to evolve, thrive, and eventually develop the intelligence to recognize Jupiter's protective role in our cosmic story. From Jupiter's protective embrace, we drift outward to Saturn, a world that embodies one of the most counterintuitive facts in planetary science. This giant, famous for its spectacular rings, harbors a secret that would astound ancient astronomers. Despite being a massive planet, Saturn is so light it would float. Saturn's average density is just 0.687 grams per cubic centimeter, about 30% less dense than water, which has a density of 1 gram per cubic centimeter. This means that if you could find a bathtub large enough, and we're talking truly cosmic proportions here, Saturn would bob on the surface like a gigantic cork. This remarkable property stems from Saturn's composition. Like Jupiter, Saturn is primarily made of hydrogen and helium, the lightest elements in the universe. But Saturn contains a higher proportion of hydrogen relative to heavier materials than Jupiter does. While Jupiter's immense mass compresses its hydrogen and helium to higher densities, Saturn, being less massive, experiences less gravitational compression, allowing its atmospheric gases to remain more expanded and less dense. The low density tells us something fascinating about planetary formation. In the early solar system, Saturn formed far enough from the Sun that temperatures were cold enough for water, ammonia, and other compounds to freeze into solid particles. These ices provided the initial solid cores around which hydrogen and helium could accumulate. Saturn's core is likely a mixture of rock and ice, but this solid center represents only a small fraction of the planet's total mass. What's truly mind-bending is visualizing this low-density giant. Saturn has a volume 764 times larger than Earth, yet its mass is only 95 times greater. If Earth were a marble, Saturn would be a beach ball that weighs less than 100 marbles, a sphere so large you could fit 764 Earths inside it, yet so light that its gravitational field at the cloud tops is only slightly stronger than Earth's surface gravity. This low density affects everything about Saturn, from its rapid rotation period of just 10.7 hours to its oblate shape. Saturn spins so fast that centrifugal force flattens it significantly. Its equatorial diameter is about 10% larger than its polar diameter, giving it a noticeably squashed appearance that's visible even in small telescopes. The low density also influences Saturn's magnetic field and internal heat generation. Despite receiving only 1% of the sunlight that Earth gets, Saturn radiates 2.5 times more energy than it receives from the Sun. This internal heat comes from gravitational contraction. The planet is still slowly shrinking and converting gravitational potential energy into heat, a process that's been ongoing since Saturn's formation 4.6 billion years ago. Saturn's rings, those magnificent structures that make it the jewel of the solar system, are possible partly because of the planet's low density and resulting gravitational characteristics. The ring particles, chunks of water ice ranging from tiny grains to house-sized boulders, orbit in complex patterns influenced by Saturn's gravitational field and the gravitational effects of its many moons. This floating giant challenges our intuitions about planets and mass. We expect massive objects to be dense and heavy, but Saturn demonstrates that size and density don't always correlate in the ways we might expect. It's a reminder that the universe operates on principles that often defy our Earth-based experiences and expectations. Saturn's low density also makes it unique among gas giants. While Jupiter is dense enough that it would sink in water, and the ice giants Uranus and Neptune are much denser due to their rocky and icy compositions, Saturn alone occupies this strange realm of planetary physics, where a world larger than 764 Earths could theoretically float in a cosmic ocean. Continuing our journey through the outer solar system, we encounter Uranus, a world so bizarre in its behavior that it seems to have forgotten the basic rules of planetary motion. While other planets spin like tops as they orbit the Sun, Uranus rolls through space like a barrel, fundamentally different from every other planet in our solar system. Uranus has an axial tilt of 98 degrees, meaning it's essentially rotating on its side. To understand how extreme this is, consider that Earth's tilt is 23.5 degrees, which gives us our seasons. Mars tilts at 25 degrees, similar to Earth, but Uranus is tilted so far over that its rotational axis lies almost in the plane of its orbit around the Sun. This means that for part of Uranus's 84-year orbit, one pole points almost directly at the Sun, while the other points away into the darkness of space. During these periods, one hemisphere experiences 42 years of continuous daylight, while the other endures 42 years of continuous night. Then, as Uranus continues its orbit, the situation gradually reverses. Imagine living on Uranus during these extreme seasons. If you were at the North Pole during summer, the Sun would circle around the sky continuously for decades, never setting. The temperature would gradually rise as the Sun climbed higher in your sky over the course of years. Then, after 42 Earth years, the Sun would finally set, not for a day, but for another 42 years of uninterrupted winter darkness. What caused this bizarre orientation? The most widely accepted theory is that Uranus suffered a catastrophic collision early in its history. A massive object, possibly as large as Earth, struck Uranus with such force that it knocked the planet completely over. This impact was so violent that it fundamentally altered the planet's rotational dynamics for the rest of its existence. But the collision theory faces some puzzles that make Uranus even more mysterious. If such a massive impact occurred, we'd expect it to disrupt any moons or rings that existed at the time. Yet Uranus has a complex system of moons and rings that appear to have formed or reformed after the hypothetical collision. The 5 major moons, Miranda, Ariel, Embriel, Titania, and Oberon, all orbit Uranus's equator. which means they orbit almost perpendicular to the planet's orbital plane around the Sun. Even stranger, Uranus's magnetic field doesn't align with either its rotational axis or its orbital motion. The magnetic field is tilted 59 degrees from the rotational axis and doesn't even pass through the planet's center. This suggests that Uranus's magnetic field is generated in an unusual way, possibly in a thin shell of water, ammonia, and methane ice surrounding the planet's core, rather than in a central dynamo like Earth's magnetic field. This bland appearance is deceptive, though. Uranus actually has some of the most extreme weather in the solar system, with wind speeds reaching up to 560 miles per hour. The planet's unusual heat distribution, caused by its sideways orientation, creates complex atmospheric circulation patterns that we're still trying to understand. The discovery of Uranus's extreme tilt was one of the first hints that planetary formation is far more chaotic and violent than early astronomers imagined. The idea that planets form in orderly, predictable ways was shattered by the realization that massive collisions can fundamentally alter a world's basic characteristics. Uranus's rings, discovered in 1977, add another layer to its strangeness. These narrow, dark rings orbit around the planet's equator, meaning they appear to stand almost vertically when viewed from Earth at certain times in Uranus's orbit. The rings are composed of some of the darkest material in the solar system, reflecting only about 2% of the light that hits them. The sideways world of Uranus reminds us that our solar system's formation was not a gentle, gradual process, but a violent, chaotic period of cosmic collisions and catastrophic events. When you spot Uranus in the night sky, it's just barely visible to the naked eye under perfect conditions. You're looking at a world that defies everything we consider normal about planetary behavior, a cosmic oddball that continues to challenge our understanding of how planets can exist and evolve. Our journey through the outer solar system brings us to Neptune, the most distant major planet and home to one of the most perplexing meteorological mysteries in planetary science. Here, in the frigid depths of space where sunlight is 900 times weaker than on Earth, winds howl across the planet's surface at speeds that shouldn't be possible. Neptune's winds reach velocities of up to 1,200 miles per hour, faster than the speed of sound on Earth. These are the fastest sustained winds measured anywhere in our solar system, even faster than Jupiter's Great Red Spot or Saturn's hurricane-force storms. What makes this phenomenon truly baffling is that Neptune receives only 0.1% of the solar energy that Earth does, yet somehow powers atmospheric dynamics more violent than any other known planet. To understand how extraordinary this is, consider the energy dynamics. On Earth, our weather systems are driven by solar heating. The sun warms different parts of our planet unevenly, creating temperature differences that drive wind and storms. The stronger the solar heating, the more energy available for weather. This is why planets closer to the sun should, logically, have more energetic atmospheres than those farther away. But Neptune shatters this logical expectation. Despite being 30 times farther from the sun than Earth, Neptune's atmosphere is in constant violent motion. The planet's deep blue appearance, caused by methane in its atmosphere absorbing red light, gives no hint of the supersonic tempest raging in its upper atmosphere. The secret to Neptune's impossible winds lies not in external solar heating, but in internal heat generation. Neptune radiates 2.6 times more energy than it receives from the sun, meaning the planet has a significant internal heat source. This internal energy comes from two primary sources: leftover heat from the planet's formation 4.6 billion years ago, and ongoing gravitational compression as the planet continues to slowly contract. But internal heat alone doesn't explain the extreme wind speeds. Holworth scientists believe Neptune's unique atmospheric composition and structure create almost perfect conditions for generating these supersonic flows. The planet's atmosphere contains water, methane, and ammonia ices in its deeper layers, with hydrogen and helium dominating the upper atmosphere. This layered structure may create extremely efficient heat transport mechanisms that concentrate energy into narrow bands of incredibly fast-moving air. Neptune's most famous atmospheric feature was the Great Dark Spot, a storm system comparable in size to Jupiter's Great Red Spot, but far more dynamic and short-lived. First observed by Voyager 2 in 1989, this massive anticyclonic storm was roughly the size of Earth and had winds circulating at 1,500 miles per hour, making it the fastest rotating storm system ever measured in our solar system. What made the Great Dark Spot even more remarkable was its transient nature. When the Hubble Space Telescope observed Neptune in 1994, the Great Dark Spot had completely disappeared, replaced by new storm systems in different locations. This rapid appearance and disappearance of massive storms demonstrates that Neptune's atmosphere is far more dynamic and unstable than the relatively stable atmospheric features on Jupiter and Saturn. Neptune's wind patterns also show characteristics never seen elsewhere. The planet has a retrograde equatorial jet stream, meaning the atmosphere at the equator rotates slower than the planet's interior, opposite to what we see on other gas giants. This backward-flowing equatorial wind reaches speeds of 900 miles per hour in the opposite direction of Neptune's rotation, creating shear forces that likely contribute to the planet's violent storm systems. The extreme wind speeds affect everything about Neptune's appearance and behavior. Cloud features race across the planet's surface, changing dramatically over periods of hours or days. The fastest moving clouds have been clocked at velocities that would carry them around Neptune's entire circumference in less than 18 hours, even though the planet itself rotates once every 16 hours and 6 minutes. These supersonic winds also interact with Neptune's magnetic field in ways we're still trying to understand. The planet's magnetic field, like Uranus's, is tilted significantly from its rotational axis and offset from the planet's center, suggesting unusual internal dynamics that may be connected to the extreme atmospheric circulation. The study of Neptune's winds also reveals something profound about energy distribution in planetary atmospheres. While we often think of planets as systems in equilibrium, Neptune demonstrates that worlds can maintain extremely non-equilibrium conditions for billions of years, continuously converting internal energy into atmospheric motion with an efficiency that exceeds our best engineering systems. When you consider that Neptune completes one orbit around the Sun every 165 Earth years, these supersonic winds have been howling for centuries. From Neptune's howling winds, we venture to the edge of our solar system to visit one of the most fascinating gravitational relationships in space, the Pluto-Charon system. Here, in the cold darkness beyond Neptune's orbit, two worlds perform an intimate cosmic dance that's unique in our solar system. Pluto and its largest moon Charon are tidally locked to each other, meaning they always show the same face to one another as they orbit their common center of mass. This isn't just unusual, it's the only known example of mutual tidal locking between a planet and moon in our solar system. To understand how remarkable this is, consider our own moon. While the moon is tidally locked to Earth, always showing us the same face, Earth continues to rotate freely, experiencing day and night cycles. But on Pluto, if you were standing on the hemisphere facing Charon, you would see Charon hanging motionless in your sky, never rising or setting, never changing position. Meanwhile, the other hemisphere of Pluto never sees Charon at all. It remains permanently hidden behind the horizon. The same is true from Charon's perspective. If you were standing on the Charon hemisphere facing Pluto, Pluto would appear frozen in your sky, never moving, never setting. Half of each world exists in perpetual view of the other, while the other half never sees its companion. This mutual tidal locking occurred because Charon is unusually large relative to Pluto, while our moon is about 1/4 the diameter of Earth. Charon is about half the diameter of Pluto. This makes the Pluto-Charon system more like a double planet than a traditional planet-moon pair. In fact, some astronomers argue it should be classified as a binary planet system rather than a planet with a satellite. The gravitational forces that created this mutual lock were immense. Over millions of years, tidal forces gradually synchronized the rotations of both bodies until they reached this perfect gravitational embrace. The process involved the conversion of rotational energy into heat through tidal friction, gradually slowing both bodies until they achieved perfect synchronization. What makes this even more fascinating is the discovery of Pluto's other moons, Nix, Hydra, Kerberos, and Styx. These smaller satellites orbit around the Pluto-Charon system's barycenter, the point in space around which both Pluto and Charon orbit. This barycenter lies in the space between the two worlds, rather than inside Pluto as it would in a typical planet-moon system. The orbital dynamics of this system are complex and chaotic. Computer simulations show that the smaller moons tumble chaotically as they orbit, their rotations influenced by the complex gravitational field created by the Pluto-Charon binary. Some of these moons may even swap orbits over long periods, demonstrating that even in the outer solar system, gravitational relationships continue to evolve. The mutual tidal locking also affects the surface features of both worlds. The constant gravitational stress creates bulges in both Pluto and Charon that point toward each other, frozen in place like gravitational fossils. These tidal bulges are permanent features, locked in position by the synchronized rotation. Recent analysis of New Horizons data suggests that the Pluto-Charon system may have formed through a giant impact similar to the Earth-Moon system, but with different results. In this scenario, a large object collided with early Pluto, and the debris from this impact eventually coalesced to form Charon. The unusual mass ratio and orbital characteristics support this collision origin theory. The Pluto-Charon system also demonstrates how tidal forces can drive geological activity. Despite being far from the Sun in the frigid outer solar system, both worlds show evidence of recent geological activity. Pluto's surface features suggest active geology within the past few million years, possibly driven by tidal heating from its interaction with Charon. This distant double world system challenges our understanding of planetary classification and formation. When Pluto was reclassified as a dwarf planet in 2006, the Pluto-Charon system became our best example of a binary dwarf planet, showing that gravitational relationships in the outer solar system can be fundamentally different from those in the inner planets. The perfect gravitational synchronization of Pluto and Charon represents one of the most stable orbital relationships in our solar system, a cosmic dance that has continued for millions of years and will persist for millions more. Two worlds forever gazing at each other across the darkness of space. Leaving our solar system behind, we venture into the realm of exoplanets, worlds orbiting other stars that challenge everything we thought we knew about planetary composition. Among these alien worlds, none is more spectacular or valuable than 55 Cancri, a planet that may be composed largely of diamond. Located 40 light-years away in the constellation Cancer, 55 Cancri is a super-Earth twice the size of our planet, but 8 times more massive. What makes this world extraordinary isn't just its size, but its likely composition. Based on spectroscopic analysis and theoretical modeling, scientists believe this planet contains more carbon than oxygen, a reversed ratio compared to Earth and most other rocky planets we know. In the extreme conditions of 55 Cancri's interior, where pressures reach millions of times, Earth's atmospheric pressure and temperatures soar to thousands of degrees. Carbon doesn't remain in familiar forms like graphite or coal. Instead, these conditions compress carbon atoms into diamond crystal structures throughout much of the planet's interior. To understand the magnitude of this diamond world, consider the economics. If 55 Cancri is indeed largely composed of diamond, its value would be approximately $26.90 nonillion. That's 26.9, followed by 30 zeros. This single planet contains more wealth than has ever existed in human history, multiplied by trillions of trillions. But before you start planning an interstellar mining expedition, remember that 55 Cancri is incredibly close to its host star, so close that it completes one orbit in just 18 Earth hours. Ein mu, meandering stals, intuis hours, wudryodenavita, wudryodenav. The planet is tidally locked, meaning one side perpetually faces the star, while the other remains in permanent darkness. Surface temperatures on the day side reach 4,000 degrees Fahrenheit, hot enough to melt most metals, and certainly hot enough to vaporize any human technology we could send there. The discovery of carbon-rich exoplanets, like 55 Cancri, has revolutionized our understanding of planetary formation and composition. On Earth and other planets in our solar system, oxygen is more abundant than carbon, leading to the formation of silicate minerals that dominate rocky planet composition. But in regions of the galaxy where carbon is more abundant than oxygen, entirely different types of planets can form. These carbon planets, as astronomers call them, would have geological processes unlike anything on Earth. Instead of silicate magmas, they might have carbide or diamond-based geological activity. Their atmospheres could contain carbon monoxide, methane, and other carbon compounds in concentrations that would be toxic to Earth life, but might support entirely different forms of biochemistry. The formation process of diamond planets, like 55 Cancri, reveals the incredible diversity possible in planetary systems. These worlds likely formed from the same protoplanetary disk as their host star, but in a region where carbon-rich materials dominated over oxygen-rich silicates. As the planet accreted material and grew larger, gravitational compression transformed much of its carbon content into diamond structures. Recent observations using the Spitzer Space Telescope have provided additional evidence for 55 Cancri-E's unusual composition. The planet's thermal emissions suggest a surface and interior composition very different from Earth-like rocky planets, supporting the diamond planet hypothesis. But 55 Cancri isn't the only carbon-rich world we've discovered. PSRJ 1719-1438b, a planet orbiting a pulsar, is thought to be an even more extreme diamond world, the compressed remnant of a white dwarf star that has been transformed into a massive diamond by the intense gravitational and magnetic fields of its pulsar companion. The existence of diamond planets has profound implications for astrobiology and our search for life in the universe. While life as we know it requires liquid water and moderate temperatures, the discovery of such exotic planetary compositions suggests that the universe might harbor forms of life based on entirely different chemistry. Carbon-rich worlds might support life forms that use silicon-carbon compounds, metal carbides, or other exotic materials as the basis for their biochemistry. These hypothetical life forms would be so different from Earth life that we might not even recognize them as living organisms. The study of diamond planets also helps us understand the chemical evolution of the galaxy. Different regions of our galaxy have different ratios of carbon to oxygen, determined by the history of stellar nucleosynthesis and supernova explosions. By studying carbon-rich exoplanets, we can map the chemical diversity of planetary systems throughout the Milky Way. From a technological perspective, diamond planets like 55 Cancri represent both ultimate treasure and ultimate challenge. Diamond is not only valuable as a gemstone, but also has remarkable properties. It's the hardest natural material, an excellent conductor of heat, and has unique electrical properties that make it useful for advanced electronics. However, the extreme conditions on these worlds make them essentially inaccessible with any conceivable technology. The combination of intense heat, crushing gravity, and vast distance makes diamond planets the ultimate example of treasure that's impossible to claim. 55 Cancri reminds us that the universe is far more creative and diverse than our Earth-based experience suggests. In the vast expanse of space, there are worlds of diamond, planets of iron rain, and atmospheres of vaporized rock, compositions so exotic they read like science fiction, but represent the spectacular reality of planetary diversity in our galaxy. From diamond worlds, we journey to an even more hostile realm, planets where the very concept of weather takes on nightmarish dimensions. Meet HD 189733b, a world where it rains molten glass blown sideways by winds reaching 4,300 miles per hour, creating one of the most hellish environments imaginable in our galaxy. HD 189733b, located 63 light-years away in the constellation Vulpecula, appears deceptively beautiful from a distance. Hubble Space Telescope observations reveal a stunning azure blue color that rivals Earth's oceans. But this similarity is purely superficial and deeply misleading. The blue color doesn't come from water, but from tiny silicate particles suspended in the planet's atmosphere, the same material that forms glass. This world is what astronomers classify as a hot Jupiter, a gas giant that orbits incredibly close to its host star. HD 1-897-33b completes one orbit in just 2.2 Earth days, circling its star at a distance of only 2.9 million miles. For comparison, Mercury orbits our Sun at 29 million miles. This proximity subjects the planet to intense stellar radiation that heats its atmosphere to over 1,800 degrees Fahrenheit. At these extreme temperatures, many compounds that exist as solids on Earth become gases. Silicates, the minerals that form sand and glass, vaporize and condense in the planet's turbulent atmosphere. As these silicate vapors cool in the upper atmosphere, they condense into tiny particles that we would recognize as glass. But these aren't gentle raindrops falling peacefully downward. The planet's extreme proximity to its star creates enormous temperature differences between the day and night sides. The day side, perpetually facing the star due to tidal locking, experiences temperatures around 1,800 degrees Fahrenheit, while the night side cools to a relatively frigid 1,200 degrees Fahrenheit. This 600-degree temperature difference drives atmospheric circulation patterns unlike anything in our solar system. These temperature gradients generate winds of extraordinary violence. Atmospheric models suggest that wind speeds on HD 1-897-33b can exceed 4,300 miles per hour, more than 5 times faster than the speed of sound on Earth. To put this in perspective, the fastest winds ever recorded on Earth during Hurricane Patricia reached 215 miles per hour. HD 1-897-33b's winds are 20 times faster than the most extreme terrestrial hurricanes. These supersonic winds carry the condensed silicate particles, essentially molten glass droplets, horizontally across the planet's surface. Instead of rain falling down due to gravity, glass particles are blown sideways with such force that they would shred any material we know. The rain on HD 1-897-33b isn't a gentle precipitation, but a horizontal barrage of glass bullets moving at hypervelocity speeds. The physics of this glass rain reveals the exotic nature of hot Jupiter atmospheres. At the extreme temperatures found on HD 1-897-33b, the boundary between liquid and gas becomes blurred. Silicate droplets may exist in a supercritical state, neither fully liquid nor gas, but something in between, carrying properties of both phases simultaneously. Spectroscopic analysis has revealed the detailed composition of this alien precipitation. The glass rain contains magnesium silicate, MiG-SiO3, similar to the mineral enstatite found in meteorites and deep within Earth's mantle. But while enstatite exists as solid crystals in cooler environments, on HD 1-897-33b, it cycles between vapor, liquid, and solid states as it moves through different temperature zones in the planet's atmosphere. The sideways glass rain creates a perpetual cycle of atmospheric violence. On the day side, intense stellar radiation vaporizes silicate materials from the planet's atmosphere and potentially from any solid surface that might exist beneath the dense gas envelope. These vapors are caught up in the massive atmospheric circulation patterns and carried toward the night side. As the silicate-laden atmosphere moves toward the cooler night side, the vapors begin to condense, forming droplets of molten glass. These droplets are immediately caught up in the hypervelocity winds and blasted horizontally across the planet's surface. Sidavong. I feed Saab. Some of these glass particles may eventually make their way back to the day side, where they're vaporized again, continuing the cycle. This glass rain world also reveals the incredible precision of modern astronomical techniques. The detection of specific atmospheric components on a planet 63 light-years away represents one of the greatest achievements in observational astronomy. Scientists use transit spectroscopy, analyzing how starlight filters through the planet's atmosphere as it passes in front of its host star to identify the chemical signatures of various atmospheric components. The study of HD 189733b's extreme weather has implications for understanding atmospheric dynamics throughout the galaxy. Many of the exoplanets we've discovered are hot Jupiters with similar extreme conditions. Understanding how these worlds develop such violent weather systems helps us model atmospheric evolution and dynamics in planetary systems very different from our own. From an astrobiology perspective, HD 189733b represents the extreme end of inhospitable conditions. Whole known form of life could survive in an environment where glass rain falls sideways at hypersonic speeds, while surrounded by temperatures hot enough to melt copper. Yet studying such extreme worlds helps us define the boundaries of habitability and understand the full range of planetary environments that exist in our galaxy. The glass rain of HD 189733b also demonstrates the incredible violence that stellar radiation can inflict on nearby planets. The intense X-ray and ultraviolet radiation from the host star doesn't just heat the planet's atmosphere, it actively strips away atmospheric material, creating a comet-like tail of escaping gas that streams behind the planet as it orbits. Recent observations suggest that HD 189733b is losing atmosphere at a rate of about 600 million kilograms per second, gradually evaporating under the intense stellar bombardment. This atmospheric escape, combined with the extreme weather conditions, makes HD 189733b a world in constant transition. A planet where glass rain and stellar winds are slowly eroding the very atmosphere that creates these extraordinary conditions. HD 189733b stands as a testament to the incredible diversity and extremes possible in planetary atmospheres, a world where the familiar concept of weather becomes an alien phenomenon of violence and beauty that challenges our understanding of what's possible in the universe. Returning to our solar system, we encounter a sobering reminder that even the most iconic and seemingly permanent features of our cosmic neighborhood are subject to change. Jupiter's Great Red Spot, perhaps the most famous storm in the solar system, is dying before our eyes. For over 400 years, this massive anticyclonic storm has been Jupiter's defining feature, a swirling tempest large enough to swallow 2 or 3 Earths. In the late 1800s, the storm measured about 25,000 miles in diameter. By the 1980s, it had shrunk to roughly 14,500 miles across. Today, the Great Red Spot measures only about 10,000 miles in diameter, less than half its historical size. At this rate of contraction, some scientists predict the Great Red Spot could become circular rather than oval within the next 10–20 years, fundamentally altering its dynamics and possibly leading to its complete dissipation. The shrinking isn't just about size, it's about power and longevity. The Great Red Spot is essentially a high-pressure storm system, rotating counterclockwise and fed by smaller storms that merge with it over time. As the spot shrinks, it spins faster, like a figure skater pulling in their arms. Wind speeds at the storm's edge have increased from about 250 miles per hour to over 400 miles per hour as the storm has contracted. What's causing this iconic storm to fade away? Several factors contribute to the Great Red Spot's decline. Jupiter's atmospheric dynamics are incredibly complex, with multiple jet streams and smaller storm systems constantly interacting. Changes in these global circulation patterns may be depriving the Great Red Spot of the energy it needs to maintain its size and intensity. Climate modeling suggests that Jupiter's atmosphere undergoes long-term oscillations and changes similar to Earth's climate cycles, but on much larger scales and longer time periods. The current shrinking of the Great Red Spot may be part of a natural atmospheric cycle that operates over centuries or millennia. The storm's interaction with Jupiter's other atmospheric features also plays a role. Polar storms and eddies can either feed energy into the Great Red Spot or steal energy from it, depending on their size, rotation, and approach angle. Recent observations have shown smaller storms being absorbed by the Great Red Spot, but apparently not providing enough energy to maintain its historical size. Jupiter's internal heat generation may also be a factor. The planet radiates more energy than it receives from the sun, and changes in this internal heat flow could affect atmospheric circulation patterns that sustain the Great Red Spot. As Jupiter continues to cool and contract over geological timescales, its atmospheric dynamics slowly evolve. The implications of losing the Great Red Spot extend beyond mere spectacle. This storm system has been a natural laboratory for studying atmospheric dynamics under extreme conditions. Its longevity has provided scientists with centuries of data about how large-scale atmospheric features can persist and evolve over time. The Great Red Spot's behavior also influences Jupiter's broader atmospheric patterns. Its gravitational and rotational effects help organize other atmospheric features and may play a role in Jupiter's complex system of colored bands and zones. If the Great Red Spot disappears, Jupiter's entire atmospheric organization could shift in unpredictable ways. Historical records suggest that Jupiter's atmosphere has experienced similar changes before. Observations from the 18th and 19th centuries describe variations in the number, size, and color of atmospheric features. Some astronomers speculate that large storms like the Great Red Spot may be cyclical phenomena that appear, persist for centuries, and then fade away, only to be replaced by new storm systems. Recent high-resolution observations by the Juno spacecraft have revealed that the Great Red Spot extends much deeper into Jupiter's atmosphere than previously thought. Its roots may extend 200 miles below the visible cloud tops. This deep structure suggests the storm is more stable than surface observations might indicate, but it also means that changes in Jupiter's deep atmospheric layers could fundamentally alter the storm's behavior. The shrinking Great Red Spot serves as a reminder that nothing in the universe is truly permanent. Even features that have persisted for centuries can change and disappear, teaching us that planets are dynamic, evolving systems rather than static objects frozen in time. Among all the remarkable facts about planets, perhaps none reveals more about humanity's relationship with the cosmos than this simple observation. Earth is the only planet in our solar system not named after a Roman or Greek deity. While our neighboring worlds bear the names of gods and goddesses, our own planet carries a name rooted in the soil beneath our feet. Mercury takes its name from the Roman messenger god, known for his speed, fitting for the planet that races around the sun faster than any other. Venus bears the name of the Roman goddess of love and beauty, inspired by the planet's brilliant appearance as the morning and evening star. Shastro, Fort Umaison. The outer planets continue this divine tradition. Jupiter, the largest planet, bears the name of the king of the Roman gods. Saturn is named after the Roman god of agriculture and time. Uranus, though discovered much later, was named after the Greek god of the sky and heavens. Neptune carries the name of the Roman god of the sea, appropriate for its deep blue color. But Earth, our planet's name, comes from the Old English word eordi and the Germanic erdi, both meaning simply ground or soil. The word shares roots with similar terms in many Germanic languages, Dutch aardi, German erdi, and Scandinavian jord. All these words point to the same fundamental concept: the solid ground beneath our feet, the dirt in which we plant our crops, the fundamental substance of our terrestrial existence. This linguistic difference reveals something profound about human perspective throughout history. When ancient peoples looked up at the night sky, they saw mysterious, moving lights that seemed divine in nature. These wandering stars appeared to follow celestial paths, disappearing and reappearing in patterns that suggested supernatural intelligence. It was natural to associate them with gods and goddesses, to see them as manifestations of divine will and power. But Earth was different. Earth wasn't mysterious or distant. It was immediate, tangible, practical. It was the realm of daily life, of farming and building, of birth and death. While the planets were objects of wonder and worship, Earth was simply home. It was the foundation of existence, so fundamental that it needed no grand mythological explanation. The naming difference also reflects humanity's gradual recognition of our place in the cosmos. For most of human history, we didn't understand that Earth was a planet at all. We saw ourselves as the center of creation, with the heavens revolving around us. The other planets were celestial objects out there, while Earth was the stage upon which the cosmic drama played out. This geocentric worldview began to change during the scientific revolution. Copernicus, Galileo, and others gradually revealed that Earth was not the center of the universe, but merely one planet among others, orbiting the sun like the rest. This revelation was so revolutionary that it literally changed our language. We began speaking of the Earth as a planet, comparable to the other worlds in our solar system. Yet, we kept the humble name. Even as we recognized Earth's planetary nature, even as we understood our world's place in the cosmic order, we retained the simple earthy name that connected us to our terrestrial origins. No committee of astronomers decided to rename our world after Gaia or Terra or some other deity. The name Earth stuck, carrying forward the agricultural, practical heritage of our species. Different cultures have their own names for our planet, many of which do invoke divine or mythological associations. In many languages, Earth is connected to goddesses of fertility and motherhood. The Greek Gaia, the Roman Terra Mater, the Norse Earth. But in English, the language that has become dominant in international science and space exploration, we've retained the humble, non-divine designation. The contrast becomes even more striking when we consider how other planets' names influence our perception of them. Mars evokes thoughts of conflict and aggression, fitting its red, desert appearance. Venus suggests beauty and romance, though the reality of its hellish surface couldn't be more different. Jupiter implies majesty and power, appropriate for the solar system's giant. Or, Tenomir. Perhaps this is fitting. Among all the worlds we know, Earth remains unique as the only one that harbors life, the only one we can truly call home. While the other planets may bear the names of gods, Earth bears the name that reflects what it truly is: the ground beneath our feet, the foundation of all human experience, the soil from which we came and to which we return. In keeping its humble name, Earth reminds us that sometimes the most extraordinary things are hidden in the most ordinary words. Of all the ways that Mars differs from Earth, perhaps none is more visually striking or counterintuitive than this. On the red planet, sunsets are blue. This remarkable phenomenon reveals the profound ways that atmospheric composition can transform our perception of a world, creating beauty in the most unexpected forms. When we think of Mars, we think red soil, red rocks, red skies. The planet's rusty appearance comes from iron oxide, essentially rust, that covers much of its surface, blown into the atmosphere by frequent dust storms. During most Martian days, the sky appears butterscotch or yellowish-brown, tinted by the fine iron oxide particles suspended in the thin atmosphere. But as the sun approaches the horizon during Martian sunsets and sunrises, something magical happens. The sky around the sun takes on a distinctly blue color, creating a phenomenon that's the exact opposite of what we experience on Earth, where sunsets paint the sky in brilliant reds, oranges, and yellows, while the sun itself appears reddish. Mars's atmosphere tells a different story. While it's also primarily composed of small gas molecules, mostly carbon dioxide, the Martian atmosphere contains a significant amount of fine dust particles that are much larger than gas molecules. These dust particles are roughly the same size as the wavelength of visible light, which creates a very different scattering behavior called me-scattering. Phi-me scattering affects all colors of light more equally, but it has a subtle preference for forward scattering, meaning it tends to scatter light in the same direction it was already traveling. During a Martian sunset, when we're looking toward the sun through a thick layer of dusty atmosphere, the dust particles preferentially scatter red and yellow light away from our line of sight, while allowing more blue light to continue traveling toward us. In the new lie, during a Martian sunset, when we're looking toward the sun through forward scattering, meaning it tends to scatter light in the same direction it was already traveling. The result is counterintuitive and beautiful. On Mars, the area around the sun appears blue during sunsets and sunrises, while the sky away from the sun takes on reddish and orange hues. It's as if someone inverted the color palette of an Earth sunset, creating an alien vista that challenges our expectations of how sunsets should look. This phenomenon was first captured by NASA's Mars Pathfinder mission in 1997, but it was the stunning images from the Spirit and Opportunity rovers, and later the Curiosity and Perseverance rovers, that truly revealed the ethereal beauty of Martian sunsets. These robotic explorers have sent back hundreds of images showing the sun setting behind Martian horizons, surrounded by halos of blue light that gradually fade to the more familiar reddish tones of the Martian sky. The blue sunsets of Mars aren't just beautiful, they're scientifically invaluable. By studying how sunlight interacts with the Martian atmosphere during different times of day and different seasons, scientists can learn about atmospheric composition, dust distribution, and weather patterns. The blue sunsets also reveal something important about Mars's atmospheric pressure and density. Mars's atmosphere is less than 1% as dense as Earth's, which means there are fewer particles overall to scatter light. This thin atmosphere allows more direct light transmission, but the dust particles that are present have a proportionally larger effect on the colors we see. Temperature variations during Martian sunsets add another layer of complexity to the phenomenon. As the sun sets, temperatures drop rapidly due to the thin atmosphere's inability to retain heat. This temperature change affects how dust particles behave in the atmosphere, sometimes causing them to settle more quickly or form different types of formations that can alter the sunset colors. The duration of Martian sunsets is also different from Earth's. Because Mars is farther from the sun and has a thinner atmosphere, the transition from day to night happens more quickly. The beautiful blue glow around the sun during sunset lasts only a few minutes before fading to the darker colors of the Martian night sky. Recent observations from Mars rovers have revealed that the color and intensity of blue sunsets vary with the seasons. During Martian winter, when temperatures are coldest, carbon dioxide from the atmosphere actually freezes out at the polar caps, making the atmosphere even thinner and potentially altering the dust distribution. These seasonal changes create subtle variations in sunset colors that help scientists understand Mars's atmospheric dynamics. The blue sunsets of Mars represent more than just a beautiful curiosity. They're a window into understanding how different atmospheric conditions can create dramatically different sensory experiences. For future human explorers of Mars, these blue sunsets will provide daily reminders of just how far from home they've traveled. While the landscapes of Mars may appear desolate and alien, the blue glow of sunset will offer moments of unexpected beauty in the harsh Martian environment, proving that even on distant worlds, nature finds ways to create wonder. Venus's volcanic nature becomes clear when we peer through its opaque atmosphere using radar imaging from spacecraft like Magellan. The planet's surface reveals a world almost entirely resurfaced by volcanic activity within the last 500 million years, relatively recent in geological terms. Unlike Earth, where plate tectonics constantly recycles the surface, Venus appears to have undergone massive, planet-wide volcanic episodes that completely renewed its surface. The sheer number of volcanoes on Venus is staggering. Scientists have identified over 1,600 major volcanic features, ranging from massive shield volcanoes larger than any on Earth to unique formations called pancake domes, circular, flat-topped volcanic structures with no Earth equivalent. These pancake domes form when highly viscous lava erupts and spreads in perfectly circular patterns, creating features that look exactly like their name suggests. What makes Venus's volcanism even more remarkable is that it occurred without plate tectonics. On Earth, most volcanoes form along tectonic plate boundaries or over hotspots, where plates move over stationary mantle plumes. But Venus shows no clear evidence of plate tectonics, yet it has experienced more volcanic activity than Earth, which suggests fundamentally different mechanisms for heat transport and volcanic eruption. The largest volcanic features on Venus dwarf those on Earth. Honam, Venus's tallest volcano, rises 5 miles above the surrounding plains and spans 200 miles across its base. Sapars Mons displays a complex system of overlapping lava flows that extends for hundreds of miles in all directions. Recent analysis of Venus's surface suggests that volcanic activity may be ongoing. The European Space Agency's Venus Express mission detected infrared signatures that could indicate recent lava flows, and some regions show surface features so well preserved that they could be only thousands of years old. If confirmed, this would make Venus one of the most volcanically active bodies in our solar system today. Venus's extreme volcanism has profoundly shaped its atmosphere and climate. The planet's dense carbon dioxide atmosphere, with crushing surface pressures 90 times greater than Earth's, likely originated from massive volcanic outgassing. The volcanic activity has also created unique atmospheric phenomena. Sulfur compounds from volcanic emissions create sulfuric acid clouds that completely shroud the planet. These clouds reflect sunlight, making Venus the brightest planet in our sky, but they also trap heat like a blanket, contributing to the runaway greenhouse effect that makes Venus's surface hotter than Mercury, despite being farther from the Sun. Radar imaging has revealed that Venus's volcanic features include formations never seen elsewhere. Coronae are circular to oval features hundreds of miles across, surrounded by concentric ridges and fractures. These mysterious structures may form when large plumes of hot material rise from Venus's interior, bulging the surface upward and creating the distinctive crown-like patterns that give them their name. The volcanic landscape of Venus also includes vast plains covered by flood basalts, massive lava flows that spread across thousands of square miles. These features suggest episodes of truly catastrophic volcanism that would have altered the planet's entire surface and atmosphere in relatively short geological periods. Understanding Venus's extreme volcanism helps scientists study volcanic processes under conditions impossible to replicate on Earth. The high temperature, pressure, and atmospheric composition on Venus create unique volcanic behaviors that expand our understanding of how planets can evolve through geological processes. The volcanic world of Venus reminds us that planets can evolve along dramatically different paths, creating landscapes of beauty and terror that exist nowhere else in our solar system. In our quest to understand remarkable worlds, we must acknowledge a truth that has revolutionized modern planetary science. Some of the most fascinating and potentially habitable places in our solar system aren't planets at all, but moons. Europa, Enceladus, Titan, and other moons have captured scientific imagination in ways that overshadow many of the planets they orbit. Europa, Jupiter's fourth largest moon, exemplifies this shift in perspective. Beneath its icy surface lies a global ocean containing more water than all of Earth's oceans combined. This subsurface sea, kept liquid by tidal heating from Jupiter's immense gravitational pull, represents one of the most promising locations for finding extraterrestrial life in our solar system. Europa's ice shell, estimated to be 15 tipped and 25 kilometers thick, shows dramatic evidence of the dynamic ocean beneath. It is plove of melee. The surface displays a complex network of ridges, cracks, and chaos terrain, where ice blocks have shifted and reformed, indicating active geological processes driven by the underlying ocean. Some areas show evidence of water plumes erupting through the ice, suggesting that Europa's ocean occasionally breaches the surface. The ocean beneath Europa's ice contains more than twice as much water as Earth's oceans, and it likely has existed for billions of years, providing ample time for life to potentially develop. The ocean floor probably contains rocky material in contact with water, creating conditions similar to Earth's deep-sea hydrothermal vents, where some scientists believe life may have first emerged on our planet. Saturn's moon Enceladus presents an even more dramatic example of active geology. This small, icy moon shoots massive plumes of water, ice, and organic compounds from its south polar region through cracks in its surface called tiger stripes. These geysers, some reaching heights of 500 kilometers, provide direct evidence of a subsurface ocean and ongoing geological activity. What makes Enceladus particularly exciting is that the Cassini spacecraft actually flew through these plumes and analyzed their composition. The results revealed not just water ice, but complex organic molecules, salts, and other compounds that suggest hydrothermal activity on the ocean floor. These ingredients, liquid water, organic compounds, and energy sources, represent the fundamental requirements for life as we know it. Titan, Saturn's largest moon, offers yet another type of remarkable world. Larger than Mercury, Titan possesses a thick nitrogen atmosphere and a complex cycle of methane and ethane that creates weather patterns, rivers, lakes, and seas. Titan is the only body in our solar system other than Earth with stable liquid on its surface, though these liquids are hydrocarbons rather than water. Titan's methane cycle mirrors Earth's water cycle in remarkable detail, pursuing mether amphors as rain that carves river channels and fills as rain that carves river channels and fills hydrocarbon seas. The largest of these seas, Kraken Mare, is larger than the Caspian Sea and contains more liquid hydrocarbons than all of Earth's oil and gas reserves combined. The complexity of Titan's chemistry extends beyond simple hydrocarbons. The moon's atmosphere undergoes photochemical processes that create complex organic molecules, some of which rain down to the surface as a kind of organic snow. These processes may be similar to those that occurred on early Earth before life emerged, making Titan a natural laboratory for studying prebiotic chemistry. Even more intriguing, recent evidence suggests that Titan may also harbor a subsurface water ocean beneath its icy crust, making it potentially habitable in two different ways, either through exotic hydrocarbon-based chemistry on its surface and through more familiar water-based chemistry in its interior. These remarkable moons have fundamentally changed our understanding of habitability in the solar system. Or previously, scientists focused on the habitable zone around stars, the region where liquid water could exist on a planet's surface. But moons like Europa and Enceladus show that tidal heating can maintain liquid oceans far beyond traditional habitable zones, vastly expanding the number of potentially habitable worlds. The study of these complex moons has also revealed that small bodies can be more geologically active than much larger planets. Enceladus, only 500 kilometers in diameter, shows more current geological activity than Mars, which is 6,800 kilometers in diameter. This activity comes from tidal forces created by gravitational interactions with their parent planets, energy sources that don't exist for isolated planets. The atmospheric and surface complexity of these moons often exceeds that of planets. Titan's atmosphere is denser than Earth's and shows more complex weather patterns than Mars. Europa's subsurface ocean may contain more diverse chemistry than Venus's surface. These moons demonstrate that size isn't always the determining factor in creating interesting dynamic worlds. Future space missions reflect this shift in scientific priorities. NASA's Europa Clipper mission and the proposed Enceladus Life Finder would specifically target these moons rather than planets. The recognition that moons can be more scientifically interesting than planets represents a fundamental change in how we approach planetary science and astrobiology. Among the most shocking discoveries in modern astronomy is the existence of hot Jupiters, massive gas giant planets orbiting so close to their host stars that they complete full orbits in just days or even hours. These worlds shouldn't exist according to our best theories of planetary formation, yet they represent some of the most common types of exoplanets we've discovered, forcing scientists to completely rethink how planetary systems form and evolve. When astronomers first developed models of planetary formation in the 1990s, the process seemed straightforward, either in the cold outer regions of protoplanetary disks, beyond what's called the snow line, water and other volatile compounds freeze into solid particles. These icy particles stick together more easily than rocky materials, allowing massive solid cores to form quickly. Once these cores reach about 10 Earth masses, their gravity becomes strong enough to capture and hold onto hydrogen and helium gas from the surrounding disk, growing into gas giants like Jupiter and Saturn. This formation process requires cold temperatures and abundant solid material, conditions that exist only in the outer regions of planetary systems, far from host stars. According to these early models, gas giants should form beyond the snow line and remain there throughout their lives. The idea of a Jupiter-sized planet orbiting closer to its star than Mercury orbits our Sun seemed not just unlikely, but physically impossible. Then came 51 Pega CB, discovered in 1995, by Michel Mayor and Didier Queloz. This planet, later dubbed the first confirmed hot Jupiter, orbits its Sun-like star every 4.2 days at a distance of only 4.8 million miles, 8 times closer than Mercury orbits our Sun. With a mass similar to Jupiter, but surface temperatures exceeding 1,800 degrees Fahrenheit, 51 pega-CB, shattered existing theories of planetary formation and launched the era of exoplanet science. The discovery of hot Jupiters revealed that planetary systems could evolve in ways far more dynamic and violent than anyone had imagined. Or if gas giants form in the cold outer regions of planetary systems, how do they end up orbiting so close to their stars? The answer lies in planetary migration, a process where gravitational interactions cause planets to spiral inward or outward from their original formation locations. Several mechanisms can drive planetary migration. The most important is interaction with the protoplanetary disk itself. As a young gas giant orbits within the disk of gas and dust around its star, gravitational forces create spiral density waves in the disk material. These waves carry away angular momentum from the planet, causing it to spiral inward toward the star in a process called Type II migration. Computer simulations show that this inward migration can be rapid and dramatic. A Jupiter-mass planet can migrate from the outer regions of a planetary system to very close to its host star in less than 100,000 years, the blink of an eye in astronomical terms. This migration continues until something stops it. Either the protoplanetary disk dissipates, the planet reaches the star's surface and is destroyed, or other gravitational influences halt the inward spiral. The discovery of hot Jupiters also revealed that planetary migration doesn't always stop at the formation of close-orbiting giants. Many hot Jupiters show evidence of continued orbital evolution through tidal interactions with their host stars. The intense gravitational forces between a hot Jupiter and its star cause both bodies to deform, creating tidal bulges that exchange angular momentum and gradually change the planet's orbit. Some hot Jupiters are spiraling even closer to their stars and will eventually be torn apart by tidal forces or consumed entirely. Others may be slowly moving outward as tidal forces work to synchronize the planet's orbit with the star's rotation. These ongoing processes mean that hot Jupiter systems are dynamic, constantly evolving environments rather than stable, long-term configurations. The existence of hot Jupiters has profound implications for planetary system architecture. As massive planets migrate inward, they can gravitationally scatter smaller, rocky planets, either ejecting them from the system entirely or pushing them into highly eccentric orbits. This process may explain why many exoplanetary systems look so different from our own solar system, with unusual orbital configurations and missing planet types. Hot Jupiters also challenge our understanding of planetary atmospheres under extreme conditions. These worlds experience intense stellar radiation that heats their atmospheres to thousands of degrees and creates powerful atmospheric circulation patterns. Hot Jupiters also challenge our understanding of planetary atmospheres under experience. The temperature differences between day and night sides, hot Jupiters are typically tidally locked, drive wind speeds that can exceed 1,000 miles per hour. The atmospheric chemistry of hot Jupiters includes phenomena never seen in our solar system. At the extreme temperatures these planets experience, molecules that normally exist as solids or liquids become gases. Metals like iron and magnesium vaporize and can condense into clouds at different atmospheric levels, creating complex layered atmospheric structures. Some hot Jupiters experience such intense heating that their atmospheres are actually escaping to space. The most extreme examples, called hot Neptunes or super-Earths, may be the remnant cores of former gas giants that have had their entire gaseous envelopes stripped away by stellar radiation. The study of hot Jupiters has also revealed unexpected diversity in planetary migration histories. Some hot Jupiters may have formed through high eccentricity migration, where gravitational interactions with other planets or stellar companions first push the planet into a highly elongated orbit. Then tidal forces circularize the orbit close to the star. Others may have migrated smoothly inward through disk interactions. The prevalence of hot Jupiters, they're found in about 1% of Sun-like stars, suggests that planetary migration is a common and important process in planetary system formation. This discovery has led to new models of solar system formation that include migration of the giant planets, helping explain puzzling features of our own planetary system, like the structure of the asteroid belt and the distribution of small bodies in the outer solar system. Hot Jupiters represent one of the most important discoveries in modern astronomy, not just because they're exotic worlds, but because they revealed that planetary formation and evolution are far more complex, dynamic, and varied than anyone imagined. These impossible planets have taught us that the universe is capable of creating planetary systems in ways that challenge our most fundamental assumptions about how worlds form and evolve. The existence of hot Jupiters reminds us that nature is far more creative than our theories, and that the process of discovery often begins with finding things that shouldn't exist according to our current understanding of the universe. While we explore exotic worlds with impossible features, one of the most profound changes happening in our solar system is occurring right beneath our feet. Earth's rotation is gradually slowing down, making our days longer with each passing century, a process that connects us to the cosmic forces that shape planetary evolution throughout the universe. The evidence for Earth's slowing rotation comes from multiple sources, but perhaps the most tangible proof lies in ancient geology and biology. Coral fossils from 400 million years ago show daily growth rings that reveal there were approximately 400 days in a year during the Devonian period. Since the length of Earth's orbit hasn't changed significantly, this means each day was shorter, about 22 hours instead of our current 24 hours. The primary culprit behind Earth's slowing rotation is tidal friction created by our moon. As Earth rotates, it drags its tidal bulges along with it. But the moon's gravity pulls on these bulges, creating a torque that acts like a brake on Earth's rotation. This same process causes the moon to gradually spiral away from Earth at a rate of about 1.5 inches per year, a process measured precisely using laser reflectors left on the lunar surface by Apollo astronauts. The rate of this rotational slowdown is remarkably consistent. Earth's rotation slows by approximately 1.7 milliseconds per century. While this seems insignificant, it accumulates over time. In 140 million years, Earth days will be 25 hours long. In 1 billion years, if the process continues unchanged, Earth days could last 30 hours or more. But Earth's rotational history isn't a simple story of gradual deceleration. Early in Earth's history, shortly after the moon forming impact 4.5 billion years ago, Earth spun much faster, completing a full rotation in just 6 hours. The moon was also much closer, appearing enormous in Earth's sky and creating tidal forces far more powerful than those we experience today. The slowing of Earth's rotation has had profound effects on our planet's geological and biological evolution. The length of the day influences everything from weather patterns to the evolution of biological rhythms. Many organisms have internal biological clocks that evolved to match Earth's rotational period, and changes in day length over geological time may have influenced evolutionary processes in ways we're only beginning to understand. Modern technology can measure Earth's rotational variations with extraordinary precision. Atomic clocks and satellite measurements reveal that Earth's rotation speed varies slightly from day to day and season to season due to factors like atmospheric pressure changes, ocean currents, and even large earthquakes. Modern technology can measure Earth's rotation to use a fubor. The 2004 Indian Ocean earthquake was so massive that it actually sped up Earth's rotation by 2.68 microseconds by redistributing the planet's mass. Distributing the planet's mass. Climate change is also affecting Earth's rotation in measurable ways. As ice sheets melt and redistribute water from the poles to the oceans, the planet's moment of inertia changes slightly, affecting rotation speed. It's like a figure skater extending their arms to slow their spin, but on a planetary scale, The gradual lengthening of Earth's days has practical implications for modern timekeeping. Since 1972, scientists have occasionally added leap seconds to our clocks to keep atomic time synchronized with Earth's actual rotation. These leap seconds are necessary because our precise atomic clocks tick away at a constant rate, while Earth's rotation varies unpredictably. Looking toward the future, Earth's rotational slowing will eventually reach an equilibrium point where Earth and the Moon become tidally locked to each other, similar to the Pluto-Charon system. In this distant future, Earth days and lunar months will both be about 47 current days long, with the Moon hanging motionless in the sky as seen from one hemisphere of Earth. However, this tidal locking is billions of years in the future, and other factors may intervene. The Sun's gradual increase in brightness as it ages will eventually make Earth uninhabitable long before tidal locking occurs. Earth's slowing rotation reminds us that even the most fundamental aspects of our planet, the length of our days, the rhythm of day and night that governs all life on Earth, are constantly changing over geological timescales. It connects us to the broader story of planetary evolution throughout the universe, where tidal forces between planets and moons continuously reshape orbital dynamics and rotational characteristics across billions of years. Beyond the ordered dance of planets around stars lies a darker, more mysterious population of worlds, rogue planets that wander through interstellar space, unbound by the gravitational embrace of any star. These cosmic nomads represent one of the most haunting and fascinating discoveries in modern astronomy, challenging our understanding of planetary formation and potentially harboring environments where life could survive in the darkness between stars. Rogue planets, also called free-floating planets or orphan planets, are planetary mass objects that either formed independently in space or were ejected from their original star systems. Current estimates suggest there may be billions or even trillions of these wandering worlds in our galaxy alone, potentially outnumbering stars themselves. The discovery of rogue planets has been one of the great detective stories of astronomy. Unlike planets orbiting stars, rogue planets emit no reflected starlight and are nearly impossible to detect directly. Most discoveries have come through gravitational microlensing, a technique that detects the slight magnification of background starlight when a rogue planet passes between Earth and a distant star. One of the most significant rogue planet discoveries was CFB-DSIR 2149-0403, located about 130 light-years from Earth. This world, with a mass 4-7 times that of Jupiter, drifts through space at temperatures around -80 degrees Fahrenheit, frigid, but not as cold as might be expected for a world receiving no stellar heating. The relatively warm temperature comes from internal heat generated during the planet's formation, an ongoing gravitational contraction. The existence of rogue planets reveals the violent dynamics of early planetary system formation. Computer simulations show that gravitational interactions between forming planets can eject worlds from their birth systems entirely. As planets migrate and their orbits evolve, close encounters can provide enough gravitational energy to launch planets into interstellar space at velocities exceeding their star system's escape velocity. Jupiter-mass planets are the most likely to become rogues because their large mass makes them effective at gravitational scattering, but they're also massive enough to retain significant internal heat after ejection. Smaller Earth-like rogue planets would be much colder and more difficult to detect, but they may be even more numerous than their giant counterparts. What makes rogue planets particularly intriguing is the possibility that some could harbor life. While their surfaces would be frozen solid without stellar heating, many rogue planets likely retain substantial internal heat for billions of years. This heat could maintain subsurface oceans beneath layers of ice, similar to the moons Europa and Enceladus in our own solar system. Some of the most exciting rogue planet candidates may actually be failed stars called brown dwarfs, objects that formed like stars but lack sufficient mass to sustain nuclear fusion. The boundary between massive rogue planets and low-mass brown dwarfs is unclear, and some objects in this intermediate range may have planetary characteristics while retaining stellar formation processes. The study of rogue planets has revealed new insights into planetary formation processes. Some rogue planets may have formed independently in interstellar space through the gravitational collapse of gas clouds, similar to star formation, but on a smaller scale. Others clearly show evidence of formation within stellar systems before ejection, retaining chemical signatures that reveal their origins. Advanced detection techniques are beginning to reveal the true population of rogue planets. The Nancy Grace Roman Space Telescope, planned for launch in the 2020s, will conduct a comprehensive survey using gravitational microlensing that could discover thousands of rogue planets and determine their abundance throughout the galaxy. The implications of widespread rogue planets extend to astrobiology and our search for life in the universe. If rogue planets can maintain habitable conditions independently of stars, the number of potentially life-bearing worlds in the galaxy could be orders of magnitude larger than previously thought. Life on rogue planets would need to rely entirely on chemical energy sources rather than photosynthesis, possibly resembling the extremophile organisms found near deep-sea hydrothermal vents on Earth. The existence of rogue planets transforms our understanding of planetary systems from ordered, stable configurations to dynamic, evolving environments where worlds can be born, ejected, and spend billions of years wandering through the darkness of space. These cosmic wanderers remind us that the universe contains worlds beyond our imagination, planets that never see a sunrise, never experience seasons, yet may harbor the conditions necessary for life to emerge and thrive in the eternal night between the stars. Mercury's tail was first discovered in the 1980s by ground-based telescopes, but its true nature and extent weren't understood until detailed observations by NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015. What astronomers found was a glowing tail of sodium atoms stretching up to 14 million miles behind Mercury, longer than the distance from Earth to Venus at their closest approach. The primary mechanism creating Mercury's tail is a process called sputtering, high-energy particles in the solar wind. Charged particles streaming away from the Sun at speeds of 250 miles per second strike Mercury's surface with tremendous force. These impacts are energetic enough to knock atoms completely off the planet's surface and launch them into space. But solar wind sputtering isn't the only process at work. Micrometeorite impacts also contribute to Mercury's atmospheric loss. The planet is constantly bombarded by tiny particles traveling at cosmic velocities, and each impact vaporizes a small amount of surface material, adding to the thin cloud of atoms surrounding the planet. A solar wind sputtering isn't the only process at work. Perhaps most dramatically, the Sun's intense ultraviolet and X-ray radiation directly strips atoms from Mercury's surface through a process called photon-stimulated desorption. The high-energy photons break chemical bonds in surface minerals, liberating individual atoms that can escape into space if they gain sufficient energy. The composition of Mercury's tail reveals the planet's surface mineralogy in unprecedented detail.
Sodium is the most prominent component because it's easily liberated from surface rocks and glows brightly when excited by solar radiation. But the tail also contains calcium, magnesium, and other elements that tell the story of Mercury's geological composition and the processes affecting its surface.
What makes Mercury's tail truly remarkable is its dynamic behavior. Unlike a comet's tail, which is most prominent when the comet approaches the Sun, Mercury's tail varies in brightness and extent based on the planet's position in its highly elliptical orbit and the intensity of solar wind activity. When Mercury is closest to the Sun, perihelion, increased solar heating and radiation pressure intensify the sputtering process, making the tail brighter and more extensive. The discovery of Mercury's tail has revealed something profound about planetary evolution. Over billions of years, this constant atmospheric loss has significantly altered Mercury's surface composition and may have contributed to the planet's unusually large iron core relative to its size. The preferential removal of lighter elements may help explain why Mercury has such a high density compared to other terrestrial planets. Mercury's tail behavior changes dramatically with the planet's orbital position. When Mercury is on the far side of the Sun from Earth, its tail points in our general direction, making it more visible from Earth-based telescopes. When Mercury is between Earth and the Sun, the tail points away from us and becomes much more difficult to observe. The length and brightness of Mercury's tail also depend on the planet's orbital velocity. Mercury moves fastest when closest to the Sun, reaching speeds of 38 miles per second. Recent observations have revealed that Mercury's tail has structure. It's not a uniform stream of particles, but shows variations in density and composition along its length. This structure results from the complex interplay between Mercury's weak magnetic field, the solar wind, and the various processes that liberate atoms from the planet's surface. The study of Mercury's tail has broader implications for understanding atmospheric loss throughout the solar system and beyond. Similar processes operate on Mars, where the thin atmosphere is gradually being stripped away by solar wind interaction. For exoplanets orbiting close to their host stars, atmospheric loss through sputtering and radiation pressure may be a dominant evolutionary process. Mercury's tail also provides a unique laboratory for studying fundamental physics processes. The interaction between escaping neutral atoms and the solar wind magnetic field creates phenomena that can't be studied elsewhere in the solar system. These interactions help scientists understand how magnetic fields affect particle motion in space environments. The tail's visibility from Earth makes it one of the few ways to study Mercury's surface composition remotely. Ground-based telescopes can observe the tail's spectral signatures to determine what elements are being liberated from different regions of Mercury's surface, providing insights into the planet's geological diversity and history. Future missions to Mercury will provide even more detailed observations of the tail phenomenon. The European-Japanese Bepi-Colombo mission, which will arrive at Mercury in 2025, carries instruments specifically designed to study the planet's exosphere and tail in unprecedented detail. Mercury's comet-like tail serves as a visible reminder of the dynamic processes shaping planets throughout the universe. It demonstrates that even small, seemingly inactive worlds can display spectacular phenomena when subjected to the intense radiation environment of their host stars. The tail is essentially Mercury slowly evaporating into space, atom by atom, creating a gossamer stream of planetary material that stretches across millions of miles of space. This remarkable feature transforms Mercury from a simple cratered world into a dynamic system, constantly interacting with its stellar environment, a planet that's literally streaming part of itself into space, creating one of the most beautiful and scientifically valuable phenomena in our solar system. Saturn's magnificent rings, perhaps the most iconic feature in our solar system, harbor a secret that has revolutionized our understanding of planetary dynamics. These spectacular structures are surprisingly young, forming only 100 million years ago, making them younger than the dinosaurs that once roamed Earth. This discovery overturned decades of astronomical assumptions. For years, scientists believed Saturn's rings were ancient structures, possibly as old as the planet itself, at 4.6 billion years. The rings seemed so permanent, so integral to Saturn's identity, that it was natural to assume they had always been there. But detailed analysis by NASA's Cassini spacecraft, which studied Saturn for 13 years before its mission ended in 2017, revealed a very different story. The evidence for the ring's youth comes from several converging lines of research. The most compelling evidence is the remarkable purity of the ring material. Saturn's rings are composed almost entirely of water ice, with only trace amounts of rocky contamination in the dusty environment of the outer solar system. Ancient ring systems should have accumulated significant amounts of interplanetary debris over billions of years, darkening and contaminating the ice. But Saturn's rings remain brilliantly white and nearly pristine, reflecting about 60% of the sunlight that hits them. This high reflectivity indicates that the ring particles have not been exposed to the space environment for very long. Computer models suggest that rings as clean as Saturn's could only maintain their purity for tens of millions of years before becoming significantly contaminated. The rings' mass also provides clues to their age. Cassini's final measurements revealed that the rings contain only about 40% of the mass of Saturn's moon Mimas, much less than previously estimated. This relatively low mass, combined with the ongoing loss of ring material to Saturn's atmosphere, suggests the rings cannot be ancient features. If they were billions of years old, they would either be much more massive or would have already disappeared entirely. So how did Saturn acquire its spectacular rings so recently in its history? The most widely accepted theory involves the catastrophic destruction of one of Saturn's moons. Computer simulations suggest that a moon roughly the size of Mimas, about 250 miles in diameter, ventured too close to Saturn and was torn apart by tidal forces. As it crossed what's called the Roche limit, the distance at which a planet's gravity overcomes a moon's internal cohesion, this destroyed moon would have been composed largely of water ice, explaining the ring's composition. The debris from this tidal disruption spread out around Saturn's equator, forming the ring system we see today. The process would have been spectacular, a moon-sized body stretching, deforming, and ultimately shattering into billions of fragments that gradually organized into the complex ring structure we observe. Alternative theories suggest the rings might have formed from a collision between two of Saturn's moons, or from the disruption of a large comet that wandered too close to the planet. In any scenario, the rings represent the remnants of a massive object or that met a violent end in Saturn's gravitational field. The youth of Saturn's rings has profound implications for our understanding of planetary system evolution. It suggests that dramatic events can reshape planetary systems even in their mature phases, billions of years after formation. The rings are not permanent fixtures, but temporary phenomena that formed recently and will disappear in the relatively near future. Current observations show that Saturn's rings are not stable. They're gradually spiraling into the planet due to gravitational interactions and electromagnetic forces. Ring material constantly rains down into Saturn's atmosphere at a rate of about 4,400 minus 8,800 pounds per second. At this rate, the rings will completely disappear in another 100 minus 300 million years, making them a transient feature in Saturn's long history. This discovery raises intriguing questions about ring systems throughout the universe. If Saturn's rings are temporary features that formed recently, other gas giants may have had spectacular ring systems in the past that have since disappeared. Jupiter, Uranus, and Neptune all have ring systems, but these are much fainter and less extensive than Saturn's, possibly representing different stages of ring evolution or different formation mechanisms. The temporary nature of Saturn's rings also means that humanity is incredibly fortunate to exist during the brief cosmic moment when Saturn displays this magnificent feature. For most of Saturn's 4.6 billion year history, the planet appeared as a relatively plain gas giant. Only during the last few million years has it worn the spectacular ring system that makes it the jewel of our solar system. Science fiction became science fact in 2011 when NASA's Kepler Space Telescope discovered Kepler-16b, a planet that orbits not one, but two stars, creating a real-world version of Luke Skywalker's home planet Tatooine from Star Wars. This remarkable world proved that binary star systems can indeed host planets, opening up vast new possibilities for planetary formation and the search for life in the universe. Kepler-16b, located about 245 light-years away in the constellation Cygnus, orbits a pair of stars that dance around each other every 41 days. The larger star is about 69% the mass of our Sun, while its smaller companion is only 20% as massive, a red dwarf that would appear distinctly orange-red to any observer on the planet's surface. Together, these two stars create one of the most spectacular sky shows imaginable. From the perspective of someone standing on Kepler-16b, the double sunset would be breathtaking. Depending on the orbital positions, you might see both stars setting together, creating a brilliant double-star sunset with overlapping colors and shadows. At other times, the stars would set separately, creating two distinct sunset events within a single day. The interplay of light and shadow from two moving light sources would create complex, ever-changing patterns across the landscape. The existence of Kepler-16b challenged fundamental assumptions about planetary formation. For decades, astronomers believed that binary star systems, where two stars orbit each other, would be too gravitationally chaotic to allow stable planet formation. The gravitational perturbations from two massive objects were thought to prevent the accumulation of material needed to build planets, either by stirring up the protoplanetary disk too violently or by ejecting forming planets from the system entirely. But Kepler-16b proved these assumptions wrong. The planet orbits both stars at a distance of about 65 million miles, taking 229 days to complete one orbit. The discovery was made possible by Kepler's transit photometry method, which detects the slight dimming of starlight when a planet passes in front of its host star. But Kepler-16b created a more complex signal. It transited both stars at different times, creating a distinctive pattern that revealed its circumbinary orbit. This detection required incredibly precise measurements, as the planet blocks only a tiny fraction of light from the already variable binary star system. Kepler-16b itself is a gas giant, roughly the size of Saturn, but with a mass similar to Neptune. Surface temperatures are estimated at around -100 to -150 degrees Fahrenheit, making it a cold, inhospitable world where any atmosphere would likely be frozen. Despite receiving light from two stars, the planet orbits far enough away that the combined stellar radiation provides less heating than Earth receives from our single sun. The planet's composition and properties reveal interesting details about formation in binary systems. The reduced heating from the distant binary stars means that volatile compounds like water, methane, and ammonia could have remained frozen during the planet's formation, possibly creating a world with a composition quite different from planets in single-star systems. Since the discovery of Kepler-16b, astronomers have found several other circumbinary planets, revealing that such worlds are not rare cosmic oddities, but a significant class of exoplanets. Each discovery has refined our understanding of the complex gravitational dynamics that allow planets to form and survive in binary star systems. The gravitational environment around binary stars creates unique challenges and opportunities for planetary formation. The competing gravitational fields can clear out certain orbital regions, creating gaps where planets cannot form stably. But they can also create resonant zones, where orbital periods lock into stable relationships with the binary star orbital period, allowing planets to survive in what might otherwise be chaotic environments. The complex lighting conditions on circumbinary planets also raise fascinating questions about how life might evolve under such circumstances. Photosynthetic organisms would need to adapt to variable light levels and potentially different stellar spectra from two different stars. The complex lighting conditions on circumbinary planets also raise fascinating questions about how life might evolve under such circumstances. The complex lighting conditions on circumbinary planets also raise fascinating questions about how life might evolve under such circumstances. The complex lighting conditions on circumbinary planets. The complex lighting conditions on circumbinary planets. The day-night cycle would be extraordinarily complex, with periods of single-star illumination, double-star illumination, and complete darkness varying throughout the planet's orbital period. The study of Kepler-16b and other circumbinary planets has also revealed new insights into planetary migration processes. In single-star systems, planets can migrate inward or outward relatively smoothly, but in binary systems, the complex gravitational field creates barriers to migration that can trap planets in certain orbital regions or rapidly eject them from the system entirely. Future observations of circumbinary planets will provide crucial tests of planetary formation theories and help astronomers understand how common these worlds might be. The James Webb Space Telescope and next-generation ground-based telescopes may be able to study the atmospheres of some circumbinary planets, revealing how the unique radiation environment of binary stars affects atmospheric composition and dynamics. Kepler-16b stands as proof that the universe is capable of creating planetary systems more exotic and beautiful than science fiction writers dared imagine. It's a world where binary sunsets paint the sky in impossible colors, where the complex dance of two stars creates lighting conditions unlike anywhere else in the universe, and where the very existence of the planet challenges our understanding of how worlds can form and survive in the cosmic wilderness. Beneath our feet, Earth harbors a dynamic system that shields us from cosmic radiation and makes complex life possible, our planet's magnetic field. But this protective barrier is far from stable, and one of the most unsettling discoveries in geophysics is that Earth's magnetic field regularly flips, with the north and south magnetic poles switching places in a process that could leave our planet temporarily vulnerable to the harsh radiation environment of space. Earth's magnetic field is generated by the motion of molten iron in our planet's outer core, Europa, about 1,800 miles beneath the surface. This churning, electrically conductive metal creates electric currents that generate the magnetic field through a process called the geodynamo. The field extends far into space, creating a protective bubble called the magnetosphere that deflects most of the charged particles streaming from the sun in the solar wind. The geological record reveals that magnetic reversals are not rare events, but regular occurrences throughout Earth's history. Over the past 20 million years, magnetic reversals have occurred roughly every 200,000, 300,000 years, on average, though the intervals between reversals can vary dramatically, from as short as 50,000 years to as long as several million years. The evidence for these reversals comes from volcanic rocks and seafloor sediments that preserve a record of Earth's magnetic field direction when they formed. When lava cools, iron-bearing minerals align themselves with the prevailing magnetic field, creating a permanent record of field direction. By studying these paleomagnetic records from around the world, scientists have reconstructed the history of Earth's magnetic field over hundreds of millions of years. The most recent geomagnetic reversal occurred about 780,000 years ago, during what's called the Brunhers-Matuyama reversal. Since then, Earth's magnetic field has maintained the same general orientation, with the magnetic North Pole located in the Arctic region. But concerning signs suggest that another reversal may be approaching, or may have already begun. Earth's magnetic field has been weakening at an accelerating rate over the past 400 years, losing about 10% of its strength since direct measurements began. The magnetic North Pole is also moving rapidly, migrating from northern Canada towards Siberia at an increasing speed of about 35 miles per year. These changes are consistent with the early stages of a geomagnetic reversal, though they could also represent normal variations in field strength. The process of magnetic reversal is neither instantaneous nor simple. Rather than flipping like a switch, the magnetic field gradually weakens and becomes increasingly chaotic over a period of several thousand years. During this transition, the field may develop multiple north and south poles, creating a complex, unstable magnetic configuration. The field strength can drop to as low as 10% of its normal value during the reversal process. Computer simulations of geomagnetic reversals reveal the incredible complexity of this process. The churning motion in Earth's outer core creates magnetic field lines that can become twisted, stretched, and tangled. When the field becomes sufficiently unstable, it can suddenly reorganize into the opposite polarity, like a rubber band that's been twisted until it snaps back in the opposite direction. The implications of a geomagnetic reversal for modern civilization could be severe. Our technology-dependent society relies heavily on systems that could be vulnerable to increased radiation exposure during a reversal. Satellites would face higher radiation levels that could damage electronic components and degrade solar panels. The increased radiation could also affect aircraft flying polar routes, potentially requiring flight path changes to protect passengers and crew. Power grids could be particularly vulnerable during a magnetic reversal. The weakened magnetic field would allow more high-energy particles to reach Earth's upper atmosphere, potentially inducing stronger geomagnetic storms. These storms can create electrical currents in power lines and transformers, potentially causing widespread blackouts similar to the 1989 Quebec blackout that left 6 million people without power for 9 hours. The biological effects of magnetic reversals remain uncertain but concerning. Earth's magnetic field helps protect the atmosphere from being stripped away by solar wind, and a weakened field during reversal could allow increased atmospheric loss. The paleontological record provides some clues about the biological effects of past reversals. Some studies suggest correlations between magnetic reversals and extinction events, though the evidence is not conclusive. What is clear is that life on Earth has survived hundreds of magnetic reversals over geological time, suggesting that while reversals may cause significant disruption, they're not necessarily catastrophic for the biosphere. Recent research has revealed that magnetic reversals may not be random events, but could be influenced by external factors. Some scientists propose that changes in Earth's rotation rate, caused by gravitational interactions with other planets, or by climate-driven changes in mass distribution, might trigger magnetic reversals. Others suggest that impacts from large asteroids or comets could disrupt the geodynamo and initiate a reversal. The study of magnetic reversals on other planets provides additional insights into this phenomenon. Mars appears to have lost its global magnetic field billions of years ago, possibly during a permanent reversal or field collapse. Venus has no significant magnetic field, possibly due to its slow rotation. These examples suggest that planetary magnetic fields are not permanent features and can be lost permanently under certain conditions. Current monitoring of Earth's magnetic field involves a global network of observatories and satellites that track field strength and direction with unprecedented precision. The European Space Agency's Swarm mission uses 3 satellites to map Earth's magnetic field in detail, providing real-time data on how the field is changing. This monitoring system would provide advance warning of an approaching reversal, though predicting the exact timing remains challenging. The possibility of an imminent magnetic reversal has sparked increased interest in understanding and preparing for this phenomenon. While we cannot prevent a magnetic reversal, understanding the process better could help us develop strategies to protect critical infrastructure and minimize the impact on modern civilization. Earth's magnetic field reversals remind us that our planet is a dynamic, constantly changing system. The protective magnetic shield that makes complex life possible is not a permanent feature, but a consequence of ongoing physical processes in Earth's interior. As we become increasingly dependent on technology vulnerable to radiation, understanding and preparing for magnetic reversals becomes crucial for maintaining our technological civilization through these inevitable planetary changes. Jupiter's gravitational dominance extends far beyond its massive bulk to encompass an entire system of worlds that rivals a miniature solar system. With 95 confirmed moons and new discoveries announced regularly, Jupiter hosts the largest and most complex satellite system of any planet, ranging from massive, geologically active worlds to tiny captured asteroids that barely qualify as moons. The 4 largest Jovian moons, Io, Europa, Ganymede, and Callisto, were discovered by Galileo Galilei in 1610 and revolutionized our understanding of the cosmos. These Galilean moons are worlds in their own right. Ganymede is larger than Mercury and has its own magnetic field. Europa harbors a subsurface ocean that may contain more water than all Earth's oceans combined. Io is the most volcanically active body in the solar system, and Callisto preserves a record of the early solar system's violent bombardment period. But beyond these 4 giants lies a vast collection of smaller moons that tells the story of Jupiter's gravitational reach and the chaotic dynamics of the outer solar system. The inner moons, including Metis, Adrastea, Amalthea, and Thebe, orbit close to Jupiter and are likely remnants of larger bodies that were shattered by impacts or tidal forces. This testo bossat forces Hawagentas. These moons are closely associated with Jupiter's ring system, either creating ring material through micrometeorite impacts or shepherding ring particles into stable orbits. The outer moons present a different story entirely. Most of these distant satellites are small, irregularly shaped objects with highly elliptical and often retrograde orbits. meaning they orbit opposite to Jupiter's rotation. These characteristics strongly suggest they are captured asteroids or comets that wandered too close to Jupiter and became trapped by its immense gravitational field. Jupiter's ability to capture passing objects demonstrates the planet's role as a gravitational vacuum cleaner in the outer solar system. Objects approaching from the asteroid belt or from more distant regions can be slowed down by gravitational interactions with Jupiter's existing moons, losing just enough energy to become permanently bound to the planet. This capture process is ongoing, and Jupiter likely gains new small moons regularly while losing others to collisions or gravitational ejection. The naming of Jupiter's moons reflects both astronomical tradition and the challenge of discovering so many small objects. The major moons bear names from Greek mythology associated with Zeus, Jupiter's Greek counterpart, his lovers, descendants, and companions. As the number of known moons has grown, astronomers have expanded to include more distant mythological figures, and some recent discoveries await official names as their orbits are confirmed and refined. Recent discoveries have been enabled by advances in telescope technology and digital imaging. Large ground-based telescopes can now detect objects as small as 1 kilometer across orbiting Jupiter, revealing a population of tiny moonlets that were invisible to earlier generations of astronomers. The Subaru telescope in Hawaii has been particularly successful in this work, discovering dozens of new Jovian moons in recent years. These small outer moons organize into distinct groups based on their orbital characteristics, suggesting they may be fragments of larger objects that were broken apart by collisions. The Himalaya group, Lysithea group, Ananke group, and Karma group each show similar orbital inclinations and distances from Jupiter, indicating common origins from the breakup of captured asteroids or comets. The dynamics of Jupiter's moon system are incredibly complex, with gravitational interactions between the planet, its moons, and the Sun creating a constantly evolving orbital dance. Some moons show large variations in their orbital periods due to gravitational perturbations from other moons. Others may be in temporary orbits that will eventually lead to collision with Jupiter or ejection from the system entirely. Jupiter's moon count continues to grow as observational techniques improve and more sky surveys are completed. The current total of 95 confirmed moons will likely increase as smaller and more distant objects are discovered. Some estimates suggest Jupiter may have hundreds of objects large enough to be considered moons, limited only by our ability to detect and track them. The Jovian moon system provides crucial insights into planetary formation and the early history of the solar system. The captured outer moons preserve samples of primitive materials from the outer solar system and asteroid belt. The large inner moons show evidence of complex geological processes driven by tidal heating from Jupiter's gravity. Understanding Jupiter's extensive moon system also has implications for exoplanet research. Many of the giant exoplanets discovered around other stars likely have similar extensive moon systems, potentially multiplying the number of worlds that could harbor conditions suitable for life. Jupiter's 95 moons transform our perspective of the giant planet from a single world to the center of a complex gravitational empire that captures, shapes, and governs satellites across millions of miles of space. In the realm of exotic planetary systems, few discoveries have captured the imagination quite like planets orbiting in systems with not 1, not 2, but 4 stars. These extraordinary worlds, existing in quadruple star systems, experience lighting conditions and gravitational dynamics so complex they push the boundaries of what we thought possible in planetary formation and orbital stability. The most famous example of a 4-sun planet is 30 Ari Borb, located about 136 light-years away in the constellation Aries. This remarkable world orbits in a system containing 4 stars arranged in a hierarchical structure, 2 pairs of binary stars that orbit around their common center of mass. The planet orbits the primary pair, while the secondary pair of stars circles the entire system at a much greater distance. From the perspective of someone standing on 30 Ari Burrow, the sky would present an almost constant celestial light show at different times in the planet's orbit, and the complex dance of the 4 stars An observer might see anywhere from 1 to 4 suns in the sky simultaneously. The interplay of multiple shadows, the varying intensities of light throughout the day, and the complex patterns of sunrise and sunset would create lighting conditions unlike anything in our solar system. The discovery of planets in quadruple star systems has revolutionized our understanding of planetary formation under extreme gravitational conditions. But 30 Ari Burv and similar worlds have proven these assumptions wrong. Computer simulations reveal that planets can indeed form and maintain stable orbits in multiple star systems if they orbit sufficiently close to one component of the system or sufficiently far from all stellar components. These close-in and wide orbital configurations can remain stable even in the complex gravitational environment of a quadruple star system. The formation process for planets in quadruple star systems must overcome extraordinary challenges. The protoplanetary disk, from which planets form, experiences gravitational torques from multiple stellar components, potentially truncating the disk or creating gaps that prevent material from accumulating. The varying stellar radiation from 4 different stars creates complex temperature gradients that affect where different types of materials can condense and contribute to planet formation. Despite these challenges, observations suggest that planets in multiple star systems may be more common than previously thought. Several other quadruple star systems have been found to host planets, including KIC 48662625, where a planet orbits one pair of stars, while 2 additional stellar companions orbit the system at greater distances. The stellar dynamics in quadruple star systems create some of the most complex orbital mechanics in astronomy. The 4 stars interact gravitationally in ways that can be described mathematically, but are nearly impossible to visualize intuitively. The stars' orbits precess, their separations change over time, and the entire system undergoes complex evolutionary changes as the stellar components age and evolve. For planets in these systems, the gravitational environment means that orbital stability is not guaranteed over long time periods. While a planet's orbit may be stable for millions or billions of years, changes in the stellar orbits or the evolution of stellar masses due to aging can eventually destabilize planetary orbits. Some planets in multiple star systems may experience periods of stability alternating with periods of chaotic orbital behavior. These varying radiation conditions have profound implications for atmospheric dynamics and potential habitability. A planet's atmosphere must be able to handle extreme variations in stellar heating, potentially requiring thick atmospheres capable of redistributing heat or specialized atmospheric chemistry to maintain stable surface conditions. The discovery of 4 sun planets has also revealed new insights into stellar formation processes. The fact that quadruple star systems can maintain stable configurations long enough for planets to form suggests that multiple star formation is more orderly and predictable than previously thought. These systems must have formed through processes that created stable stellar hierarchies, rather than chaotic, many-body interactions. Future observations of quadruple star systems will provide crucial tests of our understanding of planetary formation and orbital dynamics. The James Webb Space Telescope and next-generation ground-based telescopes may be able to detect additional planets in multiple star systems and study their atmospheric properties under these extreme conditions. The study of 4 sun planets also has implications for the search for life in the universe. While the complex radiation and gravitational environment might seem hostile to life, the multiple energy sources could potentially provide more stable, long-term heating than single-star systems. Planets with thick atmospheres might be able to average out the variable stellar heating to maintain stable surface temperatures suitable for liquid water. These extraordinary worlds remind us that planetary systems can exist under conditions far more extreme and complex than our solar system experience suggests. In a universe where 4 sun planets can exist and maintain stable orbits, the possibilities for planetary diversity and exotic worlds are truly limitless, challenging our assumptions about what constitutes a normal planetary system and expanding our understanding of the incredible variety of worlds that populate our galaxy. Just 4.2 light-years from Earth, practically next door in astronomical terms, orbits a world that could change everything we know about life in the universe. Proxima Centauri b, the closest confirmed exoplanet to our solar system, circles within the habitable zone of our nearest stellar neighbor, making it the most accessible, potentially habitable world beyond our solar system, and humanity's best target for interstellar exploration. Proxima Centauri b was discovered in 2016 through the radial velocity method, which detects the tiny wobble a planet's gravity creates in its host star's motion. The discovery was the culmination of years of painstaking observations by an international team of astronomers who monitored Proxima Centauri, a red dwarf star that's part of the Alpha Centauri system, for the subtle signs of planetary companions. The planet is remarkable, not just for its proximity, but for its potential habitability, with a minimum mass about 1.3 times that of Earth. Proxima Centauri b orbits its host star every 11.2 days at a distance of just 4.6 million miles, much closer than Mercury orbits our Sun. But because Proxima Centauri is a red dwarf star with only about 12% of our Sun's mass and 0.17% of its luminosity, this close orbit places the planet squarely within the habitable zone where liquid water could exist on its surface. The discovery of Proxima Centauri b represents a cosmic coincidence of extraordinary proportions. Of the roughly 400 billion stars in our galaxy, the fact that the very closest star to our solar system hosts a potentially habitable planet suggests that such worlds may be incredibly common throughout the universe. This proximity makes Proxima Centauri b not just scientifically fascinating, but practically significant as the most feasible target for humanity's first interstellar mission. However, the potential habitability of Proxima Centauri b faces significant challenges that highlight the complex nature of habitability around red dwarf stars. Proxima Centauri is what astronomers call a flare star. It regularly unleashes powerful stellar flares that can increase its brightness by orders of magnitude within minutes. These flares bombard any nearby planets with intense X-ray and ultraviolet radiation that could strip away atmospheric gases and sterilize surface environments. The planet's proximity to its host star also means it's likely tidally locked, with one hemisphere permanently facing the star in perpetual daylight, while the other remains in eternal darkness. This configuration creates extreme temperature contrasts that could make habitability challenging. The day side might experience scorching temperatures, while the night side remains frozen, with only a narrow twilight zone around the planet's terminator, potentially offering moderate conditions. Climate modeling of Proxima Centauri b reveals both promising and concerning scenarios for habitability. If the planet has a substantial atmosphere, global atmospheric circulation could potentially redistribute heat from the day side to the night side, creating more moderate temperatures across the planet's surface. However, maintaining such an atmosphere presents challenges. The intense stellar radiation and particle bombardment from Proxima Centauri's flares could gradually strip away atmospheric gases over geological timescales. For the planet to retain a substantial atmosphere, it would need either very strong initial atmospheric content or ongoing geological processes like volcanism to replenish atmospheric losses. Recent observations have provided additional insights into the Proxima Centauri system and the potential for habitability. In 2019, astronomers discovered a second planet, Proxima Centauri sit, orbiting much farther from the star. This outer planet, with a minimum mass about 6 times that of Earth, orbits every 5.2 years and is likely too cold to support liquid water. However, its presence suggests that the Proxima Centauri system underwent complex planetary formation processes that could have delivered water and other volatiles to the inner planet. The search for signs of an atmosphere around Proxima Centauri b has become a major focus of exoplanet research. The James Webb Space Telescope and other next-generation instruments may be able to detect atmospheric signatures during transits. If the planet's orbit is properly aligned, finding evidence of water vapor, oxygen, or other biosignature gases in the planet's atmosphere would provide compelling evidence for habitability or even the presence of life. Proxima Centauri b has also become the focus of ambitious proposals for interstellar exploration. The Breakthrough Starshot initiative proposes sending tiny, lightweight spacecraft propelled by laser beams to reach the Alpha Centauri system within 20–30 years. These miniature probes could potentially photograph Proxima Centauri b and transmit basic data about the planet back to Earth, providing our first close-up look at another potentially habitable world. The planet's discovery has profound implications for astrobiology and our understanding of life in the universe. If life can exist on a tidally locked world orbiting a flare star, it dramatically expands the types of environments we should consider when searching for extraterrestrial life. Red dwarf stars make up about 75% of all stars in our galaxy, and they have lifespans measured in trillions of years, far longer than the current age of the universe. This would tidde our feel major severe fear. This longevity could provide enormous advantages for life's development. While our sun will become a red giant and destroy Earth's habitability in about 5 billion years, Proxima Centauri will continue shining at roughly its current brightness for trillions of years. Any life that develops on Proxima Centauri b would have vast amounts of time to evolve and potentially develop intelligence. The study of Proxima Centauri b has also revealed new insights into planetary formation around low-mass stars. The presence of planets in the Alpha Centauri system suggests that planetary formation can occur successfully even in complex multiple-star environments. This finding increases the estimated number of potentially habitable worlds throughout the galaxy. Recent theoretical work has explored exotic possibilities for life on Proxima Centauri b that don't require Earth-like conditions. Some researchers propose that life could exist in the planet's atmosphere if surface conditions are too extreme, or in subsurface oceans maintained by geothermal heating. Others suggest that the boundary region between the day and night sides could provide stable conditions for surface-based ecosystems. The discovery of Proxima Centauri b has transformed our nearest stellar neighbor from a simple red dwarf star into a potentially habitable solar system that could harbor our closest extraterrestrial neighbors. Whether or not the planet actually supports life, its existence demonstrates that potentially habitable worlds exist within reach of human exploration, making the search for life beyond Earth not just a theoretical exercise, but a practical goal for future space missions. Hidden deep within the swirling atmospheres of gas giants lies a surprising secret. These seemingly gaseous worlds often contain solid cores that dwarf our entire planet. Recent missions to Jupiter and Saturn have revealed that these massive planets aren't just balls of gas, but complex layered structures with rocky metallic cores that can exceed Earth's mass by several times, fundamentally changing our understanding of giant planet formation and structure. For decades, the internal structure of gas giants remained largely mysterious. These planets' thick atmospheres of hydrogen and helium completely obscure their interiors, making direct observation impossible. Early models suggested that gas giants might have small rocky cores, or possibly no solid cores at all, with their massive atmospheres extending all the way to the center, in an increasingly compressed but still gaseous state. NASA's Juno mission to Jupiter has revolutionized our understanding of gas giant interiors. Using precision measurements of Jupiter's gravitational field, Juno revealed that Jupiter's core is not only solid, but surprisingly large and complex. The core appears to be fuzzy or dilute, a mixture of rock, ice, and metals that extends outward from the center and gradually transitions into the metallic hydrogen layer above. Jupiter's core contains an estimated 7% 25 Earth masses of heavy elements, spread throughout a region that extends roughly halfway to the planet's surface. This is far more rocky material than previous models predicted, and suggests that Jupiter's formation involved the accretion of numerous large rocky bodies, essentially a collection of Earth-sized planets merged together and then surrounded by a massive atmosphere of hydrogen and helium. Saturn's internal structure, studied by the Cassini mission during its grand finale in 2017, reveals a similarly surprising core structure. Saturn's core appears to contain 15–18 Earth masses of rock and ice, making it proportionally larger than Jupiter's core relative to the planet's total mass. Like Jupiter, Saturn's core is likely fuzzy, with heavy elements mixed throughout a substantial portion of the planet's interior. The formation of these massive cores requires a different understanding of how gas giants develop. The traditional core accretion model proposed that rocky cores form first, through the gradual accumulation of solid particles, then rapidly capture surrounding gas once they reach about 10 Earth masses. But the fuzzy, extended cores observed in Jupiter and Saturn suggest a more complex process involving the merger of multiple planetary embryos and the ongoing mixing of core material with overlying layers. These discoveries have important implications for understanding planetary formation throughout the universe. The large cores of gas giants represent reservoirs of heavy elements, carbon, oxygen, silicon, iron, and other materials forged in stellar interiors that were incorporated into planets during the early solar system's formation. The amount of heavy elements locked up in gas giant cores affects the composition of the entire planetary system and influences the types of rocky planets that can form. Computer models of gas giant formation now include processes like pebble accretion, where small particles spiral inward through the protoplanetary disk and are captured by growing planetary cores. This process can build massive cores more quickly than traditional models suggested, helping explain how Jupiter and Saturn acquired their enormous solid interiors before the solar nebula dissipated. The pressure and temperature conditions in gas giant cores are extreme beyond imagination. At Jupiter's core, pressures reach 40 million times Earth's atmospheric pressure, and temperatures soar to 20,000 Kelvin, hotter than the sun's surface. Under these conditions, familiar materials behave in exotic ways, with rocks potentially becoming metallic and ices existing in high-pressure crystal structures never seen on Earth. The magnetic fields of gas giants also provide clues about their internal structure. Jupiter's complex, multipolar magnetic field suggests that its magnetic field generation occurs not just in a thin shell, but throughout an extended region that includes parts of the dilute core. This distributed dynamo process could only occur if conductive materials are mixed throughout a substantial portion of the planet's interior. Understanding gas giant cores has implications for exoplanet research as well. Many of the gas giant exoplanets we've discovered, particularly hot Jupiters that orbit very close to their host stars, may have experienced significant atmospheric loss due to stellar heating. In extreme cases, this atmospheric stripping could potentially expose the solid cores, creating super-Earth planets that are actually the remnant cores of former gas giants. The solid cores of gas giants remind us that these seemingly simple gas balls are actually complex, layered worlds with internal structures as diverse and fascinating as the rocky planets we know better. Hidden beneath thousands of miles of hydrogen and helium lie planetary cores that represent some of the most extreme environments in our solar system, worlds within worlds that challenge our understanding of planetary formation and evolution. Among the many peculiarities of planetary systems, few phenomena reveal the violent history of our solar system as dramatically as retrograde moons, natural satellites that orbit their parent planets in the opposite direction of the planet's rotation. These backwards orbiting worlds tell stories of cosmic catastrophes, gravitational captures, and the chaotic dynamics that shaped the early solar system. Neptune's largest moon, Triton, provides the most spectacular example of retrograde motion in our solar system. This massive world, larger than Pluto and possessing a substantial atmosphere, orbits Neptune backwards, opposite to the planet's rotation and the orbital direction of Neptune's other moons. Triton's retrograde orbit is not just unusual, it's dynamically unstable and tells a story of violent capture from the outer solar system. Triton almost certainly began life as an independent dwarf planet, possibly similar to Pluto, wandering through the Kuiper Belt beyond Neptune's orbit. Sometime in the distant past, this world ventured too close to Neptune and was captured by the ice giant's gravitational field in a process that fundamentally altered both objects. The capture event was so violent that it likely destroyed most of Neptune's original moon system, with Triton's gravity scattering smaller moons into chaotic orbits or ejecting them from the system entirely. The physics of Triton's capture reveals the extreme nature of this event. For a large object like Triton to be captured into orbit around Neptune, it needed to lose a tremendous amount of orbital energy very quickly. This energy dissipation likely occurred through gravitational interactions with other objects in Neptune's vicinity, possibly including a binary companion that Triton may have originally possessed. Computer simulations suggest that Triton's capture was a rare, catastrophic event that occurred over a relatively short period in astronomical terms. Jupiter's outer moons provide additional examples of retrograde motion on a smaller scale. Many of Jupiter's distant satellites, including members of the Antares and Carme groups, orbit backwards relative to Jupiter's rotation. These small, irregularly shaped objects are almost certainly captured asteroids or comets that were gravitationally trapped during close encounters with the giant planet. The retrograde orbits of these captured moons reveal important details about their origins and the dynamics of the early solar system. Objects with retrograde orbits could not have formed in place around their parent planets. The processes that create planetary systems naturally produce satellites that orbit in the same direction as their planet's rotation. Retrograde motion is a clear signature of violent capture events or major orbital disruptions. Saturn's moon Phoebe represents another fascinating example of retrograde motion. This distant, heavily cratered world orbits Saturn backwards at a distance of 8 million miles, taking 550 days to complete one orbit. Phoebe's composition, revealed by the Cassini spacecraft, shows it's rich in organic compounds and water ice, suggesting it originated in the outer solar system, possibly in the Kuiper belt, before being captured by Saturn's gravity. The study of retrograde moons has revealed that gravitational capture is more common and complex than previously thought. The process requires very specific conditions. The captured object must approach at just the right velocity and angle, and there must be a mechanism to dissipate orbital energy to prevent the object from simply flying past the planet. Tidal forces, atmospheric drag, or interactions with existing moons can provide this energy dissipation. Retrograde orbits are inherently unstable over long time periods. Tidal forces between a retrograde moon and its parent planet work to slow the moon's orbital motion, causing it to spiral inward toward eventual destruction. Triton, for example, is gradually spiraling toward Neptune and will likely be torn apart by tidal forces in about 3.6 billion years, creating a spectacular ring system around the ice giant. The backwards motion of these moons also affects their parent planet's rotational dynamics. Large retrograde moons like Triton exert a braking effect on their planet's rotation through tidal interactions. Over billions of years, this can significantly alter a planet's rotational period and axial tilt, demonstrating how captured satellites can continue to influence planetary evolution long after their initial capture. Retrograde moons also serve as natural laboratories for studying extreme orbital mechanics. The complex gravitational interactions between retrograde satellites, their parent planets, and other moons create three-body and n-body problems that challenge our understanding of celestial mechanics. Esto, ang warning mealis piso. The study of backwards moons reveals that planetary systems are not the orderly, stable configurations they might appear to be, but rather the survivors of chaotic, violent formation processes. Every retrograde moon tells a story of cosmic catastrophe, objects torn from their original homes and trapped in alien gravitational environments where they continue their backwards dance around their captors. These rebellious satellites remind us that the solar system's current configuration is just a snapshot of an ongoing evolutionary process, where gravitational forces continue to reshape orbital relationships and occasionally capture new members into the complex gravitational ballet of planets and moons. One of the most mind-bending revelations about our home planet challenges our fundamental understanding of where Earth ends and space begins. Earth's outermost atmospheric layer, called the geocorona, extends so far into space that it reaches beyond the Moon's orbit, meaning our natural satellite actually orbits within Earth's atmosphere, redefining our concept of planetary boundaries and atmospheric extent. This extraordinary discovery emerged from careful analysis of data collected by the Solar and Heliospheric Observatory (SOHO) spacecraft over more than 2 decades. By studying ultraviolet emissions from hydrogen atoms in Earth's upper atmosphere, scientists were able to map the true extent of our planet's atmospheric envelope and discovered that the geocorona reaches out to at least 630,000 kilometers from Earth, nearly twice the distance to the Moon. The geocorona represents the outermost layer of Earth's atmosphere, where hydrogen atoms escape from our planet's gravitational field and interact with solar radiation. The existence of such an extended atmosphere seems to contradict our everyday experience of space as a vacuum. At the distance of the Moon, the geocorona contains only about 70 hydrogen atoms per cubic centimeter, an incredibly thin gas that's still technically part of Earth's atmosphere, but millions of times less dense than the air we breathe. For comparison, Earth's atmosphere at sea level contains about 25 trillion molecules per cubic centimeter. Despite its extreme thinness, the geocorona plays important roles in Earth's interaction with the space environment. Hydrogen atoms in this outer atmospheric layer absorb ultraviolet radiation from the sun, helping to shield the inner atmosphere from some forms of harmful radiation. The geocorona also interacts with solar wind particles, creating complex plasma physics processes that affect Earth's magnetosphere and upper atmospheric chemistry. The formation of the geocorona begins in Earth's upper atmosphere, where ultraviolet radiation from the sun splits water molecules into hydrogen and oxygen atoms. The lightweight hydrogen atoms gain enough energy to escape Earth's gravitational field, but they don't immediately disappear into interplanetary space. Instead, they form a vast, diffuse cloud around our planet that extends far beyond what we traditionally consider the edge of Earth's atmosphere. This discovery has profound implications for our understanding of atmospheric loss and planetary evolution. Earth has been losing hydrogen to space throughout its 4.6 billion year history, and the geocorona represents the current manifestation of this ongoing process. By studying the structure and dynamics of the geocorona, scientists can better understand how Earth's atmosphere has evolved over geological time and how it might continue to change in the future. The extended atmosphere also affects spacecraft operations in ways that weren't fully appreciated until recently. The Apollo astronauts who traveled to the Moon were actually flying through Earth's outer atmosphere during their entire journey, though the gas density was so low that it had no practical effect on their spacecraft. Modern satellites and space missions operating in the Earth-Moon system must account for this extended atmospheric presence in their mission planning and orbital calculations. So in Moondiager van Pivumbi, Tuerindia, the geocorona's interaction with solar radiation creates fascinating optical phenomena that are only visible from space. Spacecraft outside Earth's magnetosphere can observe the faint ultraviolet glow of the geocorona against the background of space, creating ethereal images that show our planet surrounded by a vast, luminous envelope. These observations have artistic as well as scientific value, providing a new perspective on Earth's place in the cosmic environment. Different planets have geocoronas of varying sizes and characteristics, depending on their atmospheric composition, mass, and distance from their host star. Venus has a hydrogen geocorona, but it's much smaller than Earth's due to the planet's lack of water and different atmospheric chemistry. Mars also has an extended atmosphere, but its lower gravity and thinner atmosphere create a very different structure from Earth's geocorona. The study of Earth's extended atmosphere has revealed that the boundary between planets and space is not sharp but gradual, with atmospheric density decreasing slowly over vast distances. This finding challenges traditional definitions of where Earth's atmosphere ends and has implications for understanding exoplanet atmospheres and their detection using current observational techniques. The geocorona also serves as a laboratory for studying fundamental atmospheric physics processes. The extreme conditions in this outer atmospheric layer, ultra-low density, intense radiation, and complex electromagnetic interactions, create phenomena that can't be replicated in Earth-based laboratories. Understanding these processes helps scientists interpret observations of other planetary atmospheres and develop better models of atmospheric evolution. Recent research has revealed that the geocorona's size and brightness vary with solar activity cycles. During periods of high solar activity, increased ultraviolet radiation splits more water molecules in Earth's upper atmosphere, potentially expanding the geocorona and making it brighter. During solar minimum periods, the geocorona contracts and becomes dimmer, demonstrating the dynamic relationship between Earth's atmosphere and space weather. The discovery has also provided new insights into the history of lunar exploration. Analysis of archived data from lunar missions reveals that instruments on the Moon's surface were actually detecting Earth's extended atmosphere throughout the Apollo era, though this wasn't recognized at the time. Future lunar missions will need to account for this atmospheric presence when conducting certain types of scientific observations. Climate change may also affect Earth's geocorona over long time scales. Changes in atmospheric temperature and composition could alter the rate of hydrogen escape from Earth's upper atmosphere, potentially changing the size and structure of the geocorona. Monitoring these changes could provide new indicators of global atmospheric evolution and climate change impacts. The extended nature of Earth's atmosphere also has implications for astrobiology and the search for life on other planets. If Earth-like planets commonly have extended atmospheres that reach far beyond their solid surfaces, detection methods that look for atmospheric signatures of life may need to account for these vast, tenuous outer layers. Understanding Earth's geocorona has practical applications for space exploration as well. Future missions to establish permanent lunar bases will operate within Earth's extended atmosphere, which could affect everything from spacecraft design to the search for lunar resources. The presence of hydrogen atoms from Earth's atmosphere, even in minute quantities, could influence scientific observations and industrial processes on the Moon. The revelation that Earth's atmosphere extends beyond the Moon fundamentally changes our perspective on our planet's relationship with space. Rather than existing as an isolated world surrounded by vacuum, Earth maintains an atmospheric presence that reaches across hundreds of thousands of kilometers, creating an invisible connection between our planet and its natural satellite that has existed throughout the entire history of the Earth-Moon system. One of the most revolutionary discoveries in planetary science is the realization that liquid water oceans exist throughout our solar system, hidden beneath the icy surfaces of moons, and possibly even within planets we once considered completely frozen. These ocean worlds have fundamentally transformed our understanding of habitability and the potential for life beyond Earth, revealing that the habitable zone around stars may be far less important than we once believed. Europa, Jupiter's fourth largest moon, harbors an ocean beneath its icy crust that contains more than twice as much water as all of Earth's oceans combined. This subsurface sea, kept liquid by tidal heating from Jupiter's immense gravitational pull, may be 150 kilometers deep, far deeper than any ocean on Earth. The energy from tidal flexing also drives geological activity that could create hydrothermal vents on Europa's ocean floor, providing chemical energy sources that could potentially support life. Enceladus, Saturn's sixth largest moon, provides even more dramatic evidence of subsurface oceans. Massive geysers of water, ice, and organic compounds erupt from fractures near its south pole, shooting material hundreds of kilometers into space. The Cassini spacecraft flew through these plumes and detected not just water ice, but complex organic molecules, salts, and other compounds that suggest active hydrothermal processes on the ocean floor. Ganymede, Jupiter's largest moon and the largest moon in the solar system, also harbors a subsurface ocean. Hubble Space Telescope observations of Ganymede's auroras revealed the telltale signature of a salty ocean beneath the moon's icy surface. This ocean may be sandwiched between layers of ice, creating a complex internal structure with multiple ice and liquid layers. Even more surprising is the growing evidence for oceans on worlds we never suspected. Callisto, Jupiter's second largest moon, shows signs of a subsurface ocean based on magnetic field measurements. Titan, Saturn's largest moon, likely has an ocean beneath its icy crust, in addition to its famous hydrocarbon lakes on the surface, making it potentially habitable in two completely different ways. The outer solar system continues to surprise us with ocean worlds. Triton, Neptune's largest moon, may harbor a subsurface ocean despite its incredible distance from the Sun. Even Pluto, reclassified as a dwarf planet, shows evidence of a possible subsurface ocean that could be maintained by radioactive heating from the decay of elements in its rocky core. These discoveries have completely revolutionized the concept of habitability in our solar system. Previously, scientists focused on the Goldilocks zone around stars, the narrow band where temperatures allow liquid water to exist on a planet's surface. But subsurface oceans can exist far beyond traditional habitable zones, maintained by tidal heating, radioactive decay, or other internal energy sources rather than stellar radiation. The implications for astrobiology are staggering. If our solar system contains multiple ocean worlds, each potentially harboring billions of years of stable liquid water environments, the number of habitable environments in the universe could be orders of magnitude larger than previous estimates suggested. Every gas giant with large moons could potentially host multiple ocean worlds in its satellite system. These subsurface oceans may offer advantages over surface oceans for the development and preservation of life, protected from harmful radiation and asteroid impacts by kilometers of ice. Subsurface environments could provide stable conditions for billions of years. The discovery of ocean worlds has also revealed new types of potentially habitable environments. The sulfur-rich environment around Io's volcanic activity, the hydrocarbon chemistry of Titan's surface and subsurface, and the high-pressure conditions in deep subsurface oceans create possibilities for life based on chemistry very different from Earth's biology. Future missions are specifically designed to explore these ocean worlds. NASA's Europa Clipper mission will study Europa's ocean and search for signs of habitability, while proposed missions to Enceladus could sample the plumes directly to search for signs of life. These missions represent humanity's best opportunities to discover extraterrestrial life within our own solar system. The abundance of ocean worlds in our solar system suggests that water, the essential ingredient for life as we know it, is far more common throughout the universe than we ever imagined. Rather than rare, precious exceptions, ocean worlds may be the norm rather than the exception in planetary systems throughout the galaxy. These hidden seas transform our solar system from a collection of mostly barren worlds into a diverse array of potentially habitable environments, each offering unique conditions where life might emerge, evolve, and thrive in the darkness beneath the ice. Our journey through mind-blowing planetary facts concludes with perhaps the most unsettling revelation of all. After centuries of astronomical observation and decades of space exploration, we still can't agree on what constitutes a planet. The 2006 redefinition by the International Astronomical Union that reclassified Pluto as a dwarf planet remains one of the most contentious decisions in modern astronomy, revealing that our understanding of planetary classification continues to evolve as rapidly as our discovery of new worlds. So dears constant, the redefinition by the International Astronomical Union that reclassified Pluto as a dwarf planet remains one of the most contentious decisions in modern astronomy, revealing that our understanding of planetary classified Pluto as a dwarf planet remains one of the most contentious decisions in modern astronomy, revealing that our understanding of planetary classification continues to evolve as rapidly as our... The controversy began innocuously enough, with improved telescopes revealing that Pluto, discovered in 1930, was much smaller than originally thought. When astronomer Mike Brown discovered Eris in 2005, an object in the outer solar system larger and more massive than Pluto, the astronomical community faced a crisis. Either Eris should be considered the 10th planet, or something fundamental about planetary classification needed to change. The IAU's response was to establish 3 criteria for planetary status. A celestial body must orbit the Sun, have sufficient mass to assume a roughly spherical shape, and have cleared the neighborhood around its orbit of other objects. This third criterion proved to be Pluto's downfall. Unlike the 8 traditional planets, which gravitationally dominate their orbital regions, Pluto shares its orbital space with thousands of other objects in the Kuiper belt. But this definition immediately sparked fierce debate that continues today. The cleared the neighborhood criterion is problematic because it's not precisely defined and depends on factors like distance from the sun and time since formation. Earth hasn't completely cleared its orbit. It shares space with asteroids at Lagrange points and constantly encounters meteoroids. Jupiter, despite being the solar system's gravitational vacuum cleaner, hasn't cleared all objects from its orbital zone. Many planetary scientists argue that the IAU definition focuses too heavily on orbital dynamics rather than the intrinsic properties that make worlds interesting. Alan Stern, principal investigator of NASA's New Horizons mission to Pluto, has been a vocal critic of the definition, arguing that classification should be based on geological and physical characteristics rather than orbital mechanics. The discovery of exoplanets has further complicated planetary definition. We've found objects that clearly formed like planets, but wander through space without orbiting stars, rogue planets that don't meet the IAU's first criterion. We've discovered massive objects orbiting stars that form through stellar processes, but have planetary masses, brown dwarfs that blur the line between stars and planets. Some objects orbit multiple stars, challenging our star-centric definition of planetary systems. Recent proposals for alternative definitions highlight the ongoing controversy. Some scientists advocate for a geophysical planet definition that would classify any object massive enough to be roughly spherical as a planet, regardless of what it orbits. This would make our Moon, Europa, Ganymede, and dozens of other worlds planets in their own right, potentially increasing our solar system's planet count to over 100. Others propose mass-based definitions that would classify objects based on their formation mechanisms, distinguishing between objects that formed through accretion in protoplanetary disks versus those that formed through stellar processes. First, stellar processes. This approach would help clarify the boundary between massive planets and failed stars, but it relies on formation history that's often difficult to determine observationally. The cultural and educational impact of the Pluto controversy demonstrates how deeply planetary classification affects public perception of astronomy. The decision to reclassify Pluto generated more public outrage than perhaps any other astronomical ruling in history, with textbooks needing revision and planetariums updating their displays. The phrase dwarf planet itself creates confusion. Many people assume it means a small planet rather than a distinct category of celestial object. Different space agencies and astronomical organizations continue to use varying classification systems. NASA often refers to Pluto as a planet in educational materials, while maintaining the official IAU classification in scientific contexts. Some planetary scientists have simply abandoned formal classifications in favor of describing objects by their physical characteristics and formation histories. The ongoing debate reflects deeper questions about the nature of scientific classification. Should categories be based on historical precedent, physical properties, formation mechanisms, or orbital characteristics? How do we balance scientific precision with public understanding and educational simplicity? These questions become more pressing as we discover increasingly exotic objects that don't fit neatly into existing categories. The Pluto controversy has also revealed the democratic nature of modern astronomy. Unlike historical periods, when a few prominent astronomers could define astronomical terminology, the modern astronomical community includes thousands of researchers with different specialties and perspectives. Reaching consensus on fundamental definitions becomes increasingly challenging as our knowledge expands and diversifies. Looking toward the future, the discovery of new types of celestial objects will likely force continued evolution in planetary classification. The James Webb Space Telescope and upcoming extremely large telescopes will discover objects with properties we haven't yet imagined, potentially requiring entirely new categories and definitions. Objekter wyniąd tinetry. Ukimlich serie steadedfreby of new types of celestial objects will likely force continued evolution in planetary classification. The persistent controversy over planetary definition serves as a perfect ending to our exploration of mind-blowing planetary facts. It reminds us that astronomy remains a dynamic, evolving field, where even our most basic assumptions about celestial objects continue to be challenged and refined. In a universe where planets can be made of diamond, rain glass sideways, and orbit 4 stars simultaneously, perhaps the most mind-blowing fact of all is that we're still discovering what it means to be a planet. The definition of a planet remains a work in progress, reflecting humanity's ongoing quest to understand and categorize the incredible diversity of worlds that populate our universe. We've journeyed through 31 mind-blowing facts that shatter everything we thought we knew about planets. From ice on the closest world to the sun, to glass raining sideways on distant exoplanets. From Earth's magnetic field that regularly flips to rogue planets wandering alone through space. From diamond worlds worth more than all human wealth, to moons more interesting than the planets they orbit. Each fact reveals a universe far stranger and more wonderful than our Earth-based intuitions could ever imagine. Mercury has a comet tail. Venus spins backwards. Mars has blue sunsets. Jupiter acts as our cosmic protector. Saturn would float in water. These aren't science fiction fantasies. They're the spectacular reality of planetary science. Perhaps most remarkable is what these discoveries tell us about the nature of scientific knowledge itself. We're still debating what makes a planet a planet. We're still discovering that our own atmosphere extends beyond the moon. We're still finding ocean worlds throughout our solar system. The universe continues to surprise us. Every answer reveals new questions. Every discovery challenges our assumptions. And in that endless capacity for wonder and revelation lies the true magic of exploring the cosmos. The planets we thought we knew have become alien worlds full of impossible beauty. Which of these planetary revelations shocked you the most? Was it the sideways glass rain, the diamond worlds, or perhaps the discovery that we're still redefining what makes a planet? Share your thoughts in the comments below. I love hearing which cosmic facts blow your minds. If this journey through impossible worlds has ignited your curiosity about the universe, I'm grateful you joined me for this exploration. Consider subscribing for more mind-expanding cosmic discoveries, and hit that like button if these planetary revelations left you seeing our solar system in a completely new light. The cosmos holds infinite mysteries waiting to be uncovered. Ready to explore another chapter of our universe's incredible story? Our complete cosmic collection awaits your discovery. Click here to continue your journey through the wonders that surround us in space.